Physics is about studying the laws of nature, so how nature works. Through the years, we've learned a lot about how nature works. And currently we have theories that are incredibly successful. One of the theories is the theory that describes gravity. So it was originally developed by Newton and then improved by Einstein. Einstein gave us the current equations that govern the behavior of space-time. We'll discuss perhaps a bit more what space-time is made of, or well, what the theory of Einstein tells us about space-time. So that's one very successful theory. It explained... I'm Juan Maldacena. I'm the Carl Feinberg Professor here at the Institute for Advanced Studies. My field of research is in trying to understand the fundamental laws of nature, trying to develop theories that connect space-time and quantum mechanics. And the main objective is to understand the beginning of the Big Bang. Physics is about studying the laws of nature, so how nature works. Through the years, we've learned a lot about how nature works. And currently we have theories that are incredibly successful. One of the theories is the theory that describes gravity. So it was originally developed by Newton and then improved by Einstein. Einstein gave us the current equations that govern the behavior of space-time. We'll discuss perhaps a bit more what space-time is made of, or well, what the theory of Einstein tells us about space-time. So that's one very successful theory. It explained things like the expansion of the universe, the formation of black holes. It's phenomena that before the theory was introduced, where people even didn't think about them. And on the other hand, we have the whole set of theories that describe matter, the behavior of matter and the structure of matter. And these theories were the current version, well, especially the version that is quantum mechanical, started being developed in the beginning of the 20th century. And the quantum is very important for the description of matter. It's what keeps matter stable and prevents it from collapsing, prevents atoms from collapsing, and so on. And this theory was further developed through the 20th century, and it's now come to what we call the standard model of particle physics. So it's basically the basic structures, basic constituents of matter. So matter is made out of little small particles that behave according to the laws of so-called quantum mechanics. What is remarkable is that this list of constituents is very small, so a very small number of particles make up all the matter that we see. Small particles. Of kinds of particles. So we have the particles that the electron is one of them, and then we have the particles that make up the nuclei of the atom. Within the nuclei there are some particles called quarks, but they're small little particles. For most of matter they are made out of just two kinds, so-called up and down quark. And then there are some particles that mediate the forces between them, the photon or the electromagnetic waves and so on. And then the weak force and the strong force. The strong force keeps the nucleus together. And with these particles and these forces we can describe all of matter. Now, we know it experimentally, and the latest experiment was the experiment in the Large Hadron Collider, which discovered the so-called Higgs boson. That was one of the missing particles in the standard model, and so now we have a whole set of particles that describes everything. I briefly told you about the particles that make up most ordinary matter, but there are other unstable particles which are similar. The structure gets replicated a few times, so now we have a complete set of particles with a logically consistent theory that uses the structure of something called relativistic quantum mechanics. So relativistic quantum mechanics. So it's quantum mechanics plus the principle of special relativity. So we can discuss perhaps special relativity a little more. Mm-hmm. So let me discuss perhaps these theories a little more, and then we can go on into discussing perhaps the more current issues. First, we have these notions space and time, right? So in principle, space and time seem totally disconnected from each other. So we have a very intuitive notion of space, while time looks a little more mysterious to us, and, but something different from space. So the first point I would like to explain is why physicists talk about space-time, why they put these two words together. Why don't they talk about space, temperature, space, I don't know, price of soy or whatever. So they talk about these two things because the way you perceive time depends on how you are moving through space. So if you have two observers who are moving relative to each other, the two observers perceive time differently. So if you have a clock here, another clock that is moving, this second clock will appear to this observer as moving slower than the clock has at rest. And the other observer will see the other clock also moving slower. And this can happen because space and time sort of get mixed by motion. This is the consequence of a principle, which is the principle that light, the speed of light is constant for these two observers. This is something that is not totally intuitive. So if you have one observer that is stationary, and you have a light beam that travels this way, and you have another observer that moves in this direction, naively, according to your intuition, you would expect that this observer should see the light moving slower, right?
Yes.
If instead of talking about the light beam, we were talking about the train, that would be the case, right? But it turns out that experimentally, the speed of light is constant, so it's the same for all observers. Yeah. So if you had if instead of a train we had a beam of light, the two observers, one is stationary and the other is moving, both would see the light going at the same speed. So the light would be moving this way, and this happens because the rate of how time and space are perceived by the two observers is different. So the price you have to pay for this constancy of the speed of light is that time is now relative. So in the theory of special relativity, the speed of light is absolute, but time is relative. Time is relative to who's measuring it, right? Time is relative. The flow of time depends on how you are moving through space-time. So it's similar to, let's say, space, right? So space, so if we are standing in space, there is some direction we call forward and some direction we call to our right? But if you have another person who's looking in a different direction, what's forward to him and what's to the right is different, right? So it's this exactly the same, but for moving observers. So you have two moving observers. What one calls time and space is different from what the other calls time and space.
Yeah.
So that's why it's more convenient to think about space-time as something that is both time and space, and that thing is the same for both. What one calls time and space is different, but space-time is the same, right? It's the universal structure on which particles move, right? So the laws of physics have to have this symmetry of the constancy of speed of light, and the fact that the laws of physics should be independent of how you're moving. And when you combine quantum mechanics and this principle of special relativity, you get the modern theory of particle physics. You get the structure, which is called quantum field theory, and using special cases of this structure, putting in which particles you have and the interactions and so on, you get the models for particle physics. And they are incredibly successful, and they describe all the experiments that you can do. Right, so let me first say a few words about general relativity. So, according to our intuition, so space is sort of absolute, and there is some pre-existing space where particles move and the objects move. That's probably the theory of Newton we learned in school, that planets move and so on. They are moving in some space that was pre-existing, and it's not affected at all by the motion of these planets. But in the theory of general relativity, what Einstein postulates is that space or space and time, because they have to come together because of the principle of special relativity. They are actually a structure that is dynamical, so it can be bent by the presence of matter. And he further says that the force of gravity is due to this bending of space-time. So this is a new, very interesting conceptual idea. And again, it describes gravity as we see it, and it describes deviations from Newton's gravity. It describes new things that were not known at the time of Einstein, like the expansion of the universe, the formation of black holes in extreme circumstances. And well, some of its predictions have now been confirmed, like the discovery of gravity waves very recently, just a week ago, it was announced. Yeah, that's pretty exciting and very interesting.
Did you know about that they were going to announce this?
Yeah, there were rumors that they were going to announce it, but yeah, of course the experiment had been going for a couple of decades. The gravity waves were going on for a long time, but the experiments trying to detect them also took a lot of effort. And so that's also again a dramatic confirmation of both Einstein's theories, and moreover the existence of black holes. And this theory of special relativity, of general relativity, well, Einstein derived equations, but then there was a lot of research trying to understand the solutions of the equations, the physical interpretation of the solutions. For example, black holes were really only understood in the 60s, just even theoretically. And then understanding them better then led to understanding what things you should look for in the sky, and indeed some objects in the sky were recognized as probably candidates for black holes, and now we have this gravity wave detection, which appears to come from the collision of two black holes. Well, that's what the model to describe it. We've only seen, they only announced one collision. Probably as they see more, it will become more and more convincing. So that's all about Einstein's theory of relativity. So Einstein's theory of general relativity is a theory where space-time is dynamical. It's something that moves. It's not a static thing. It's an actor in physics somehow. It's not the stage on which physics happens, but it is the stage for all particle physics, for all the matter and so on. You have a space-time, and then matter moves in that space-time. But also space-time reacts to the presence of matter and moves itself. In cosmology, this expansion of the space-time is very important. Space-time expands and it cools because of that expansion. So the expansion of space-time is very important for getting to the universe, what it is, and the structure of matter to what it is. This expansion is important for, cooling the universe, and then further, the force of gravity creates the structures that we have in the universe, such as galaxies and planets and so on. And it is important for explaining nature as we see it. But Einstein's theory of relativity is in some sense incomplete, because in the sense that you can, if you start out with some initial conditions which are reasonable, the system evolves and creates so-called singularities. So you can solve the equations, and you find situations where the curvature of space-time becomes infinite. So this happens, for example, when a black hole collapses. In the interior of the black hole there is a region with infinite space-time curvature. So if space-time becomes so curved, and so the force of gravity somehow becomes infinite there. If you were to fall in there, you would be ripped apart. We don't have a theory that, the current theories like general relativity and particle physics do not explain what happens in that situation. And so those are the theories we have. I think maybe we can make a small, because my family is coming in, and maybe I want to tell them to be quiet. Yeah, so the Einstein theory works very well for many things we observe, but the equations themselves fail in certain situations. So one situation is when matter collapses in a black hole. So in the interior of the black hole we get a region with very high curvature, and if if you were to fall in there, it would be ripped apart. And the equations don't allow us to derive what happens to matter when that happens. And another interesting situation is if you evolve the equations backwards and you try to find out what happened in the very beginning of the Big Bang, also the current theories cannot explain what happened. So there, again, the expansion would be so rapid that space expanding so rapidly that you cannot derive what happens. The equations themselves, the curvature becomes infinite, and the equations fail. Well, the main reason for this inconsistency is the fact that the Einstein's theory is a so-called classical theory, which is a good theory when things are very big, but when basically you are at very short distances, you have to take into account the quantum. In the same way that matter at long distances can be described also classically, but when you go to short distances, you have to describe it using the quantum mechanical description. Space-time is similar. When you go to very short distance in space-time, you also would need a quantum mechanical description. So for matter, when we go to short distances, we go to the atoms, the elementary particles, and so on. For space-time, we should go again to something which would be like the atoms of space-time. And so we think that if we went to such a theory, we could do this. We could perhaps understand the Big Bang or these situations which we cannot understand. I can't define the atoms of space-time. We're trying to find what they are. And one idea that is wrong is the idea that there would be atoms at each different location in space and so on. So space-time is not like continuum matter, because one important property that was understood theoretically is that when you have the number of configurations in a region of space-time, that number of configurations does not grow like the volume as it would with ordinary matter. So the number of atoms, somehow, whatever they are, of space-time, we know that their number grows like the area of the surface rather than the volume. And so that's an interesting property of these so-called atoms of space-time. So by atoms of space-time, I mean, well, basically a vague idea, but I tried to motivate it in this way, the search for a theory that describes space-time at the quantum mechanical level, so using the laws of quantum mechanics. The laws of quantum mechanics are laws which are intrinsically probabilistic, so that's the main difference from the laws of classical physics. You know the initial conditions, you can then calculate what will happen in the future. No, in quantum mechanics you can do experiments, but the result, you can prepare the initial conditions always in the same way, but the results of the experiments will be different. Each time you do the experiment, you get a different answer. And all you can predict according to quantum mechanics is not the precise answer of the experiment, but the probability distribution for the different answers. So you doing an experiment is like flipping a coin, and you can calculate and you can say, well, maybe I'll get 50% one result, 50% of the time one result and 50% the other, or maybe it's 30, 70, and so on. And quantum mechanics allows you to calculate those percentages, but quantum mechanics doesn't allow you to give definite answers to some questions. And it is intrinsically this way. So, well, I certainly I'm not the first to ask this question. So this question was asked many years ago. Probably Planck was the first to realize that there was a connection between the quantum and gravity, and at some point gravity would fail, and calculated what distance scale it would fail. So that was maybe a century ago. And since then, people have had various ideas. We're thinking about this problem, and it's a problem that is hard to access experimentally directly, because this distance at which the quantum is important is super tiny. So it's much smaller than the smallest distances we can see today with accelerators. So I'm part of a group of people who are trying to investigate this from the theoretical point of view, trying to find the structure, mathematical theory that would put these two things together. And, we are trying to do something similar to what Einstein did when he joined special relativity with Newtonian gravity. So he realized that the gravity theory of Newton was not consistent with this idea that the speed of light is the maximum speed of propagation of signals, and that it should be the same for all observers. And putting those two things together, he managed to create a structure, the structure of general relativity. So here we are trying to replicate that, and from theoretical points of view, try to find the connections between the quantum and space-time. We're not 100% sure, but we are confident that we have a high probability, and the question is so interesting that we should try to investigate it. So what gives us some confidence that we are in the right path is that we're not investigating this in the vacuum or without. We now have some very concrete theories. The nicest one is the theory of string theory. That is a theory basically under construction, but that works very nicely in some situations, and that manages to join the quantum with space-time. And it's a theory under construction and a theory which is continued to be developed. And string theory. So it seems to capture, at least it seems to connect the quantum with space-time in a very interesting way. And by investigating string theory, people have found very interesting mathematical relations that are true in mathematics. They found the connections between different physical theories. For example, between the theory of strong interactions and some theories of space-time. And the fact that these connections were found gives us some confidence that at least the structure that we're investigating is interesting and rich, and it could be the answer to this question of quantum gravity, which is really the main question we're trying to answer. For us it's difficult to find the equations but I think what I'm trying to convey is the problem we are trying to understand, and I think the problem is understandable. It's just joining two theories of physics that are out there and putting them together. So they are not completely compatible with each other, and in the history of physics, when there were two kinds of theories that were not quite compatible, and you find a structure that puts them together, it might be the right structure. So string theory is the main tool and the main thing that we are investigating, and we think that it is, if it's not the right structure, it's probably close to the right structure. It could be a stepping stone to the right structure. So string theory might sound complicated, but it's something that someone who's doing his PhD in physics can learn in a year, a couple of years. It's like playing the piano, right? You're not going to be able to play the piano in 5 minutes. So someone can tell you, you have to press keys and so on, but you won't be able to play the piano or to produce nice music. And so here also it takes a while to familiarize yourself with the ideas. And one reason it's hard is because you really have to learn a lot of the physics that precedes it. You have to learn well general relativity. You have to learn well the theory of interacting particles, and you have to do this. So no, what makes a physical theory true as a theory of physics is comparison with experiment, right? The string theory today is a mathematical structure. So it's a mathematical structure which has some physical interpretation, but we don't yet know whether it's the right theory of physics. We think it's in the right track, and we are motivated enough to continue studying it. And but that doesn't make it true. That just makes it a very interesting mathematical theory. Mainly string theory is a theory with some laws and so on that can describe space-time at the quantum mechanical level, so using the laws of quantum mechanics, and that it reduces to Einstein's theory for big distances. That's its main advantage. Now maybe you are asking why is it called strings? This comes from the fact in one of the old versions. This comes from the fact that in one formulation of the theory you have little tiny vibrating loops of string. So instead of having particles which are point-like, as we have in theory of particles, ordinary particles, the elementary objects are little strings, one-dimensional objects. And that's and using those, you can describe ripples of space-time interacting, or those gravity waves that we discussed before in the experiment. When they interact in a quantum mechanical way, they can do so in a way that does not generate any inconsistency. Well, I've been researching a certain relationship between string theory and particle physics. There's a relationship which is part of these connections that I was describing before, that string theory led to. And so this is a connection between theories of gravity in the interior of a space-time and a theory of particles on the boundary of a space-time. So in this relationship, the idea is that the so-called atoms of space-time of the interior are like particles on the boundary. That's roughly one way to say it. Another analogy people make sometimes is the idea of a hologram. A hologram is a two-dimensional photographic plate that when you illuminate it with light, you see a three-dimensional picture. So the idea is that you can have the dynamics of these particles on the boundary of space-time, so far away, can have an alternative description as objects moving in the interior, subject to the force of gravity. Yeah, so the real atoms would be on the boundary, the real elementary particles, let's say, and then we get some effective description, approximate description in terms of a space-time in the interior. So in this picture, space-time emerges as an approximation, approximation due to the dynamics of lots of particles, in the same way that properties of macroscopic objects come from similar approximations, like the viscosity of water, or just the behavior of water waves and so on, comes from the collective motion of many of the constituent molecules, right? Yeah, so this idea is the idea that you can describe gravitational physics or dynamics of space-time at the quantum level, which is something we don't understand too well how to do, in terms of a theory of particles that lives on the boundary of that space-time. The theory of particles is very similar to the theory of particles we use for particle physics, or some similar to the theories we use even in ordinary quantum mechanics. So that's this connection, and it connects, for example, black holes to thermal systems of particles at finite temperature. And if you assume, so it's a conjecture that these two things are related, and it's a conjecture that people have worked a lot on, and they found lots of evidence that it is correct, at least in very specific cases. So it's a conjecture that leads to it's a conjecture between two, let's say, mathematical theories. One is the mathematics of string theory in these spacetimes, or quantum mechanical dynamical spacetimes, as described through string theory, and ordinary theories of particle physics. And so in many cases we can approximately describe each of the two sides and then check mathematically that they are correct. But the idea is to understand this further, to understand better what this implies for space-time, and how to build better theories of space-time. In particular, how to solve some of the problems we have with black holes. So black holes are understood reasonably well with the theory of with Einstein's theory of relativity. But black holes have also give rise to some quantum mechanical effects. Well, more precisely, once you take into account quantum mechanics, black holes can start to emit a kind of radiation that Hawking discovered. He discovered this theoretically. It's called Hawking radiation. And so this implies that black holes, they form, and then they start emitting this radiation, so they emit a kind of soft glow. And just to highlight how surprising this radiation is, so black holes were called black because they don't emit any light. I mean, everything that goes in has to fall in, and nothing can be emitted, cannot get out. But this radiation is something that is somehow getting out. And so you can even have the paradoxical situation of having a white black hole. So if you had a black hole which is tiny, very tiny, the size of the wavelength of light, or the size of a bacterium, roughly speaking, that black hole will look white to our eyes. Now, these black holes don't form naturally in nature. So the black holes that form naturally in nature are very big and have a very low temperature. But if you could form such a tiny black hole, theories predict that it should look white. So here you see that a little bit of a conflict between Einstein's theory of relativity. The beginning of a conflict, you see. One says that it should be black, and the other one says it should be white, right? And here you see the beginning of some slight conflict between the two. And if you go a bit deeper in, there are some laws of, let's say, thermodynamics that should apply to black holes, to any object that emits thermal radiation. This radiation is thermal, so it gets emitted at a certain temperature. And that's why you needed to make it very small to make it look white, because the temperature becomes higher the smaller the black hole is. So a small black hole is hotter than a bigger black hole. And so as you make the black hole smaller, it gets hotter, right? And if you apply to it the laws of thermodynamics as we usually understand them, they seem to hold for such black holes. But they seem to be in some conflict with another fact we know from general relativity, which is that if you solve the Einstein's equations in a black hole, there is a surface that we call the horizon, which is a surface basically dividing the outside and the inside. It's an imaginary surface, it's not a real surface. It's kind of point of no return. So if you cross the horizon in the interior, you cannot send any signal to the outside. So you cannot even escape. You will be doomed to fall into the singularity. But you don't feel anything when you cross the horizon. So it's a perfectly reasonable surface. And so that's what Einstein's theory predicts. And this fact seems to somehow be in some conflict with these thermal properties of black holes. And how to fully resolve this conflict is one of the things I and some other people are working on. Well, I would say that it's been mostly investigating this relationship between the interior and the boundary, and also trying to understand these puzzles with black holes, these problems with black holes, quantum aspects of black holes. Yeah, probably in terms of, well, we imagine formulas and their properties, and we make a little mental image for these formulas. For example, already for Einstein's theory of relativity, you have to imagine space-time as some kind of membrane and so on. Well, I imagine it for example, it's a classical space-time, for example, as a membrane, and a quantum one, a membrane that is fluctuating. Those are the kind of mental images that we... Well, space-time is like a membrane, right? That has certain shape and has some dynamics, so the shape can change. And if you get very close, this membrane has some oscillations and some structure, right? And that's what we have at short distances. I mean, yeah, that's a picture that is more or less standard for how to think about this. Now, one of the interesting things that we've been trying to understand, and we are not, well, many people have begun to notice, is that there is some connection between a certain property of quantum mechanics called entanglement. So entanglement is a funny property, funny kind of correlation you can have in quantum mechanical systems, which are in some sense stronger than classical correlations. And so before we discuss the fact that in certain quantum mechanical systems you cannot predict the answer to certain experiment, right? So you can sometimes find 50% chance of one and 50% chance of the other answer. And you can have systems where you have two particles and they are separated, and you do an experiment here and you have 50% chance of the outcome, of each outcome, and you can do another experiment here and you have again 50% chance of any outcome. But it might turn out that the outcomes of the two experiments are correlated. So let's say the experiment is like flipping a coin, right? It comes out heads here, and then it also comes out heads here. and comes tails here, it also will come out tails here. So they're perfectly correlated. That's an example of a classical correlation. Entanglement is the fact that you can also measure another property at the same time. So of this coin, which is not heads or tail, but let's say the color. Well, this is a bad analogy because a property is quantum mechanical that cannot be measured at the same time as the original property. Right? That's one of the features also of quantum mechanics, that sometimes you can have two properties which you cannot measure at the same time. So you can either ask this coin whether it's heads or tails, or whether it says black or white, but you cannot ask whether it's black and whether it's tails, whether it's heads or tails. This is not perfect analogy because our classical variables are not of this kind. They are not sort of mutually incompatible. But you can do that with this quantum, let's say, properties. And again, you can have two particles so that if you now measure not only whether it's heads or tails, but also black or white, you have the same correlation, perfect correlation with the other. And that's some kind of correlation that is not possible in classical physics, but it's possible in quantum physics. Yeah, even though that there is a big distance. But again, with classical correlations, you can have these correlations because you prepare the two coins first, and then you took them apart, and then you look at it. So in classical physics, there is no problem with this correlation. What is interesting is that you can have a correlation between observables that are mutually incompatible locally. Right? By incompatible, I mean that either you measure one or the other, but nevertheless, you have the correlation. So entanglement was a surprising property of quantum mechanics when it was first noticed. It was noticed in a paper by Einstein, Podolsky, and Rosen in the 1930s, and this was a property, and now it's a quite central notion for quantum information theory, and people are using it in more practical ways to build. It would be essential for building quantum mechanical computers and so on. But it also seems to be connected with the connections in space-time. So things that are closer together in space-time are more entangled with each other. So, in some sense, when you have the quantum field theory vacuum, so the vacuum in the theory of particle physics, if you were to split it in two parts, the fundamental degrees of freedom or quantum variables that describe it are quite entangled with each other. And we think that in some circumstances, if you take two separate systems and you entangle them very strongly, so you could also generate some kind of quantum because you can generate, a geometric connection between them in some cases. So in some sense, through the entanglement is connected to the connectivity of space-time. So you can, So let's start with time, right? So time is what a clock measures. So now this sounds like a circular definition, but of course what's not obvious is that different clocks made in different ways measure the same time, right? But it turns out that if you have different kinds of clocks and you make them, they will all measure the same. They'll measure the same. They'll give the same answer, and that you can synchronize clocks and they stay synchronized and so on. So that it looks like there is something that is being measured by these clocks. So this something is the abstraction we call time, right? We have the time we feel psychologically, which is not a perfect clock, but certainly agrees with more precise physical clocks. But all clocks that measure time are made out of physical particles, and that's how we measure time. That's how we define it. And so it's an abstraction that is the thing that all these clocks are measuring. What is space? So, space is somehow the distance between let's say the nothingness that exists between two objects. Right? Now, it's what's missing when you go into a crowded bus. Or that's and so that's space. And now what is relativity? So let's first discuss special relativity. So before, when I was discussing time, I said that all clocks measure the same time. And that is only true for clocks that are stationary. So if you have a clock here and a clock here, and both stay at rest relative to each other, then they will measure the same time. But if you have a clock here and another clock moving, right, they will measure a different time. And relativity, so special relativity, that tells us how different is this other time that the clock measures. So it's a simple law for how to find out what that. And so the theory of relativity is the theory that postulates that the speed of light is constant. It's absolute. So he could also have called it absolute something. Well, you could replace light by other things like gravity waves also propagate at this speed. So more precisely, I should have said it's the maximum speed of propagation of signals. So the idea is that there is a maximum speed for the propagation of signals. And it so happens that light propagates at this speed. If you had a massive particle, it will generically propagate at a lower speed. But if you try to push a massive particle to move it faster and faster and faster, you could not make it move faster than this maximum speed, which also coincides with the speed of light. Yeah, and different observers would measure exactly the same speed. Well, it's not an explanation about how life started, but how the beginning of space-time started, right? How time originated and what happened in the beginning of the Big Bang. And we are trying to understand it because that's something we don't know. So science is always about pushing the boundaries. We don't. It's not just the fact that we don't know how it happened, but even we don't have it in theory that is self-consistent that could describe it. So we are even trying to find theories that could in principle describe a Big Bang. Then we'll have the problem of finding, well, that's the way our Big Bang actually happened. So that's why we think that this problem may be solved by thinking about it and finding the theory and then perhaps making some new predictions that we could test experimentally. The idea is to make a theory, and maybe the theory that you can make a theory which had a time before. Maybe you can make a theory that where time actually starts in the Big Bang and does not have any meaning before it, so that the question doesn't have a meaning. And we don't know what the right answer is, so that's what we're trying to find out, whether it's consistent. So people imagine, maybe there was a time before and somehow we went through the Big Bang, but these are just words. There are no self-consistent equations that can, where you can have such a thing. And if you try to make a theory where, the universe was contracting and then expanding again, for example, they violate some principles that we think should be true in the theory of quantum gravity. Well, I guess as I started learning more about physics, I started recognizing where the boundaries of physics were. And there are boundaries of physics in many directions, in the direction of very complex systems, in very different directions, but this is one of the directions in which we see a boundary. And so I wanted to go to the frontier in this direction, right? So I guess the physics are trying to always expand, push the frontier further and further away. I see confusion. I see lack of understanding, the idea is to find patterns in this confusion and to move forwards to understand things that we currently don't understand, bit by bit. So usually you advance one step at a time, and you can get a little further and a little further. Certainly we were trying to find this answer, and we really want to get the answer. And sometimes you feel, maybe it's close, but then you realize, maybe they made a mistake. And it's all happening also, not personally, but within a community of researchers who's trying to find this. And you criticize the ideas of others, and others criticize your ideas, and in this way you make progress, because it's a difficult problem, and you need insights from many people that know different aspects of theoretical physics or physics in general, and can inform this. Well, there might be another intelligence in our universe who has already figured out this. it has figured this out and has understood these problems. But at least it's not known to us. I mean, we are the only known intelligence in the universe, the only known being that is trying to understand the universe. So we are just expanding. When I say expanding the frontier, it's just understanding equations better, understanding laws of physics better. But these entities are very simple things. I mean, one of the features of physics is that I think it's amazingly interesting, is how simple the fundamental physics laws are. Of course, you might say, well, if it takes a couple of years to understand it, and you need to study, or maybe more, maybe you need to study physics for 5 years to understand them. Why are you saying they are simple? But they are simple in the sense that the actual laws that govern their motion and so on are really simple. So you don't have to come up with rules and lots of books and so on. It's been very different than the laws that you find in, that the senators and people produce, where there are exceptions here and there, and there is, here there is a very simple statement, and this is followed by everything we know. So, it's true to the extent we suddenly have been able to experimentally verify, and the statements are simple. They're in a language which is unfamiliar. They're in a language which takes a long time to learn, and that's what takes a long time. It's just to learn this language in which to formulate the laws, but once the laws are formulated, they're in a very simple way. I think the general relativity is probably the most beautiful theory, because it translates physics into geometry, and this is a very nice theory. We don't know how to make such a beautiful theory out of quantum mechanics, let's say, but maybe it will exist at some point. As a child, I was watching my father, for example, fixing the washing machine and trying to learn how to do it myself. And by, again, understanding how everyday objects work, like the washing machine, the car, little radio, and so on, you learn a little bit about technology and how technology exploits the laws of physics. And that got me interested in understanding the laws of physics, which underlie technology, and seeing how far they are understood and what things are known, what things are not known. And as a child, I was mostly interested in technology and how things worked. Then when I was in high school, I was a little more interested in the laws of physics and chemistry. Mainly taking things apart and seeing how they worked. That's basically the process. It's taking them apart, putting them together. It's just learning to fix household appliances. I was always curious in understanding how things work. I mean, how does the TV work? How does the radio work? What's the actual principle it uses, right? I think I know the basics. Wouldn't know all the details, I guess, of technology, which are, again, the TV or any simple or any machine, even simpler perhaps. It's better to think about a simpler machine first. It has different parts and they work together. Each part is there for a reason, and they work together to make the machine work, right? Most of our everyday machines are, the television is made out of electronic circuits that move currents around, and they do. They show the light on the screen and so on, and that makes the television work, and you have to understand how that is made. Maybe when I was perhaps from 8 to 12, we would be doing this thing of taking machines apart and putting them together. My dad liked to do this himself, so my dad always liked to fix things. He was very practical, and he liked the challenge of fixing it. And then sometimes you don't know how it works, so it's nice to have to fix something you don't know exactly how it works, and then you manage to understand how it works. I was able to do that in the past. Now cars got more complicated. I don't know, this car hasn't broken down recently, so I can't tell for sure. But it's thinking, it's discussing, it's learning what other people are thinking, and reading what other people write, and trying to make progress, right? No. I'm reading what other people write. I'm listening to other people's ideas and presentations and discussing with my colleagues, writing formulas. And I guess the thinking normally, you try to, these problems sound very vague and grand, but we try to think on very concrete problems where we can make progress, right? So there are the questions that are extremely interesting but almost impossible to solve. There are questions which are perhaps too easy to solve, and we try to be in between. So try to find the most difficult or most interesting question that you can actually say something useful about. And lots of thinking is trying to focus on such questions, as try to imagine very simple toy models or simple models where we could say something new. Yeah. So it's this thing that I was saying before, that you do a step at a time. So we have to figure out where we do the next step. So the next step is in something we more or less know, but moves us in the right direction, from which we can get a better view for what the next step would be. Well, I think during the day, and mostly I would say in my office, talking to other people. Normally, when you talk to other people, you get new ideas, and usually many times new ideas come together. We certainly write articles with other people, and this is important. I mean, most of my articles are with other people. So. Well, certainly I guess you have to be a little bit obsessive sometimes to work on these problems, because you want to think about this problem and you have to ignore other things. I mean, it's easy to get distracted and think about something else when you are not making progress. So if you're trying to solve a problem and you're not making progress, it's easy to get distracted. But sometimes you need to keep trying to find solutions to that problem you initially set out to do. Be slightly obsessive about it, and then you can make some. Well, I mean, it could be some other interesting idea in some other slightly different field. Or, I mean, sometimes it's good to be distracted. Maybe the problem you're trying to solve was bad, and so it's balance. The process is not that you write down a formula and it is true, right? So normally in physics, the process is that for some physical theory to be true, it has to be compared to experiment, and it's checked against the experiment, and then we become more sure that it's probably true. Can always be some other experiment that contradicts it, but as many experiments agree with it, you feel more and more confident. Yeah, many times a lot of our work sometimes is to derive some mathematical relations, like. And the reason for this, that some of our works is mathematics, is because the laws of physics are written in this mathematical language, and sometimes even laws which are in principle simple, like these equations of Einstein, which are simple to write down, but they're very difficult to solve. So you need either computers and with some ingenious ideas to solve the equations. But once you find, for example, the solution of the equation, you can check that it is a solution. So, and then it becomes a true solution. So that's an example where that's you could say, well, it's mathematics, right? It's within so if you assume the equations are the correct description of physics, this is a solution of the equation. Okay. Exactly, yeah. So before we were talking about the language in which these laws are written, and this is a language that is fairly mathematical. Yes. And so you need to know enough mathematics to be able to understand the. Yes. Well, there are many areas of our everyday life where we don't necessarily we don't use math. I don't know if I want to learn the piano. Math is not very useful. Or if I want to play soccer, I don't know, learn to play soccer better. Math is not very useful. You just have to practice playing soccer, right? So, or if I want to cook better, my lunch, or cook a nice meal, math is also not very useful. So there are lots of areas, but I don't know, playing soccer and sports. If I like mathematics because of some aspect, well, I like some aspects of mathematics because it's first it's a nice tool to describe physics, and I certainly like it. It's interesting. And mathematics is also a subject on its own that is huge. I know a little bit of mathematics, and I try to learn the mathematics that I think would be useful for this problem. And sometimes people need to invent some new mathematics to solve this problem. Well, that's true. I mean, we all know what our strengths are, and we try to do an activity where we can really use our talents, right? yeah, suddenly I would be a very bad interviewer. I know what the other person is thinking or trying to guess it. But yeah, we all do these various talents. Just our natural, well, or we develop certain talents. And part of our lives, we continue developing them, and we get better at that. Those sub areas. Yeah, I'm trying to remember what the story of the mountain was.
That if you live in a mountain, in a valley,
Yeah.
and you have no reason to go up on the mountain because you cannot grow corn.
Oh yeah. This was. Yeah, I think the original question was whether this is useful for anything, or what are the technological applications of this research or this area of research. And this area of research doesn't have a direct technological application that we know of. So we do it because we want to know and we want to understand. And an analogy is that to think that we have, let's say, a town that lives in a valley, and the valley is fertile, and they grow corn and they grow their food in the valley, and there's a nearby mountain, and there are some mountains surrounding the valley, and someone might decide to go up the mountain just to see what's there. Now the expedition of going up the mountain might be totally useless for growing better corn, or you will not plant anything nice in the mountains. But suddenly going up the mountain might give you a better view of the valley, might help you understand where this valley is located. And it might allow you to see another valley, but this is not guaranteed. Maybe there are all mountains and there's no other valley. But it's only part of the curiosity of seeing where we are and to extend the frontier to really understand better where we are sitting in the universe. Yeah. And this is one direction in which we can go, and certainly that's what it's like a mountain that is there, and we're trying to go to the summit and be able to understand. The summit is understanding the Big Bang singularity, so understanding the beginning of the Big Bang. And we're trying to climb this mountain. Well, we don't know because we don't have a view of the mountain from outside, so we only know that we are climbing. So I think we are confident we are climbing. We are not going down. So.
Superclusters are among the largest known structures in the observable universe. The Virgo supercluster, also known as the local supercluster, is 110 million light-years in diameter. It contains 4,000 luminous galaxies, organized into 100 galaxy groups and galaxy clusters. The Virgo supercluster's volume is approximately 7,000 times larger than our local group, and 100 billion times larger than the Milky Way. For the first time, we are at a distance where we can see the galaxies are not just evenly distributed throughout space. In this picture, each galaxy is a point of light. And these points are crowded together into galaxy clusters. And these clusters are crowded together into galaxy clouds. And these clouds of galaxy clusters are grouped up into the supercluster. Let's take a look at some of the galaxies in the Virgo supercluster. This image of the barred spiral galaxy NGC 4314 shows the entire galaxy, including the bar of stars bisecting the core and the outer spiral arms, which begin near the ends of the bar. And that's normal enough. But this Hubble image reveals clusters of infant stars that formed in a ring around the core. This close-up view by Hubble also shows other interesting details in the galaxy's core. Dust lanes, a smaller bar of stars, dust and gas embedded in the stellar ring, and an extra pair of spiral arms packed with young stars. These details make the center resemble a miniature version of the spiral galaxy itself. As the A77 is a spiral galaxy containing a supermassive black hole. The X-ray images and spectra obtained using Chandra show that a strong wind is being driven away from the center of the galaxy at a rate of about 1.6 million kilometers per hour. That's 1 million miles per hour. This wind is likely generated as surrounding gas is accelerated and heated as it swirls towards the black hole. A portion of the gas is pulled into the black hole, but some of it is blown away. High-energy X-rays produced by the gas near the black hole heat the outflowing gas, causing it to glow at lower X-ray energies. These results help explain how an average-sized supermassive black hole can alter the evolution of the entire host galaxy. This is a unique view of a galaxy tilted edge-on to our line of sight. The image highlights the galaxy structure, the subtle reddish bulge surrounding a bright nucleus, a blue disk of stars running parallel to the dust lanes, and a transparent outer halo. The dust lane is slightly warped compared to the disk of stars. This warp indicates that NGC 5866 may have undergone a gravitational tidal disturbance in the distant past by a close encounter with another galaxy. We'll use this galaxy, along with several others in the Virgo supercluster, to develop our final cosmic distance ladder rung, redshift. You may recall that we covered redshift in our segment on planetary nebula, where we used the shift in hydrogen spectral lines to determine the radial velocity of a celestial object. NGC 5866's redshift indicates that it is moving away from us at just under 1,000 kilometers per second. That's 617 miles per second. This is a 1993 image of the grand design spiral galaxy M100, taken with Hubble's Wide Field Planetary Telescope Camera 1, which was part of an original suite of instruments launched aboard Hubble in 1990. Because of a malfunctioning flaw, the galaxy appears blurred because it cannot be brought into a single focus. In celebration of the 25th anniversary of the first astronaut mission to service the Hubble Space Telescope, a comparison photo made by Hubble's Wide Field Camera 3 was released. The improvement was both critically important for Hubble's science mission, and it made for a significantly better picture. One of the ways we constructed the form of our home Milky Way galaxy is to examine galaxies that are similar in shape and structure. Spiral galaxies like NGC 3949, pictured in this Hubble image, fit the bill. Like our Milky Way, this galaxy has a bluish disk of young stars peppered with bright pink star birth regions. In contrast to the blue disk, the bright central bulge is made up of mostly older, redder stars. Here's a look at a pair of galaxies. NGC 4647 is the spiral galaxy in the upper right. M60 is the huge elliptical galaxy. On the edge of M60, there is an ultra-compact galaxy known as M60 UCD1. New Hubble observations have found a supermassive black hole with a mass of 20 million suns at its center. M60 UCD1 is a tiny galaxy with a diameter of only 300 light-years, containing some 140 million stars. This is 500 times smaller than the Milky Way, but its supermassive black hole is 5 times more massive than ours. This shows just how significant this black hole is, and it leaves open the question about just how a black hole this large could have been created in the first place, given the small number of stars in its galaxy. NGC 1427A is a bright dwarf irregular galaxy on the outskirts of the Fornax cluster. It is similar to the large Magellanic Cloud orbiting our Milky Way. It is plunging headlong into the cluster at nearly 600 kilometers per second. That's nearly 400 miles per second. 1427A will not survive long as an identifiable galaxy passing through the cluster. Within the next billion years, it will be completely disrupted, spilling its stars and remaining gas into the intergalactic space within the Fornax cluster. Most galaxies form new stars at a fairly slow rate, but members of a rare class known as starburst galaxies blaze with extremely active star formation. NGC 3310 is forming clusters of new stars at a prodigious rate. There are several hundred star clusters visible in this image as the bright blue diffuse objects that trace the galaxy's spiral arms. Each of these star clusters represents the formation of up to about 1 million stars. NGC 4013 is another spiral galaxy similar to our own Milky Way. This Hubble picture reveals, with exquisite detail, huge clouds of dust and gas extending along as well as far above the galaxy's main disk. The galaxy is larger than Hubble's field of view, and the image shows only a little more than half of the object. Zwicky 18 is classified as a dwarf irregular galaxy and is much smaller than our Milky Way. The concentrated bluish-white knots embedded in the heart of the galaxy are two major starburst regions where stars are forming at a significant rate. The wispy blue filaments surrounding the central starburst regions are bubbles of gas that have been blown away by stellar winds and supernova explosions from a previous generation of stars. This gas is now heated by intense ultraviolet radiation from hot young stars. Besides the bluish-white young stars, white-reddish stars also are visible. These stars are thought to be around 10 billion years old. NGC 4522 is a spectacular example of a spiral galaxy that is currently being stripped of its gas content by its strong central winds. A number of newly formed star clusters that developed in the stripped gas can be seen in the Hubble image. The picture highlights the dramatic state of the galaxy with an especially vivid view of the ghostly gas being forced out of the center. Bright blue pockets of new star formation can be seen to the right and to the left of center. Here we are zooming into NGC 4710 in the Virgo cluster. This magnificent giant galaxy is tilted edge-on to our view from Earth. This perspective allows astronomers to easily distinguish the central bulge of stars from its pancake-flat disk of stars, dust, and gas. When staring directly at the center of the galaxy, one can detect a faint, ethereal, X-shaped structure. Such a feature, which astronomers call a boxy or peanut-shaped bulge, is due to the vertical motions of the stars in the galaxy's bar and is only evident when a galaxy is seen edge-on. NGC 1316 is one of the brightest ellipticals in the Fornax galaxy cluster. The Hubble Space Telescope enabled uniquely accurate measurements of a class of red star clusters inside the galaxy. Astronomers conclude that these star clusters constitute clear evidence of the occurrence of a major collision of two spiral galaxies that merged together a few billion years ago to shape NGC 1316 as we see it today. In 1995, the majestic spiral galaxy NGC 4414 was imaged by Hubble as part of the KEY project on extragalactic distance scales. An international team observed this galaxy on 13 different occasions over the course of 2 months. Based on their discovery and careful brightness measurements of Cepheid variable stars, the KEY project astronomers were able to make an accurate determination of the distance to the galaxy, 62 million light years. The Hubble Space Telescope captured a display of starlight, glowing gas, and silhouetted dark clouds of interstellar dust in this image of the barred spiral galaxy NGC 1300, a prototypical barred spiral galaxy. Blue and red supergiant stars, star clusters, and star-forming regions are all well resolved in the spiral arms, and the dust lanes trace out fine structures in the disk and the bar. Hubble reveals a majestic disk of stars and dust lanes in this view of the spiral galaxy NGC 2841. A bright cusp of starlight marks the galaxy center. Spiraling outward are dust lanes that are silhouetted against the population of whitish middle-aged stars. Much younger blue stars trace the spiral arms. Notably missing are pinkish emission nebula, indicative of new star birth. It is likely that the radiation and supersonic winds from fiery, superhot young blue stars cleared out the remaining gas and hence shut down further star formation in the regions in which they were born. This picture shows a bubble in the center of a galaxy's disk. The structure is more than 3,000 light-years wide and rises 3,500 light-years above the galaxy's disk. This is a close-up view of the bubble. Gaseous filaments at the top of the bubble are whirling around in a vortex and are being propelled into space. Eventually, this gas will rain down upon the galaxy's disk, where it may collide with gas clouds, compress them, and form new generations of stars. Here's a very interesting galaxy. It is as large as the Milky Way, but it contains only 1/200th the number of stars. Given the object's large size and faint appearance, astronomers are classifying it as a ultra-diffuse galaxy. Note the galaxies behind it and further away. This is literally a see-through galaxy. Current dark matter theory has it that galaxies form around dark matter. So researchers were surprised when they discovered this galaxy has hardly any dark matter at all. Measuring the motion of 10 giant globular clusters, astronomers found their velocities to be consistent with the estimated mass of the visible matter. There was no need to assume the presence of dark matter. Astronomers have competing theories about how this could happen. We still have a lot to learn. Hannes Verwep is one of the strangest space objects ever seen. A mysterious glowing green blob of gas is floating in space near a spiral galaxy, IC 2497. The object is so huge that it stretches more than 44,000 light-years to 136,000 light-years from the galaxy's core. It turns out that it's part of a 300,000 light-years long tidal tail that wraps around IC 2497. Our current understanding is that this part of the tail was illuminated by a high-energy beam created by matter falling into the galaxy's central black hole. Their unmistakable emerald hue is caused by ionized oxygen, which glows green. Though the universe is full of spiral galaxies, no two look exactly the same. NGC 3982 is striking for its rich tapestry of star birth, along with its winding arms. The arms are lined with pink star-forming regions of glowing hydrogen, newborn blue star clusters, and obscuring dust lanes that provide the new material for future generations of stars. NGC 5584 contains Cepheid variables and one recent Type 1a supernova. As you know, we use these two standard candles as reliable distance markers to measure the universe's expansion rate. 5584 was one of the 8 galaxies astronomers studied to measure this rate. In total, the project analyzed more than 600 Cepheid variables, including 250 in 5584. This Hubble image shows NGC 4639, a spiral galaxy located 78 million light-years away in the Virgo star cluster. The blue dots in the galaxy's outlying regions indicate the presence of young stars. Among them are older, bright Cepheid stars. After using Cepheids to calculate the distance to 4639, the team compared the results to the peak brightness measurements of supernova 1990N, a Type 1a supernova located in the galaxy. Once again, Type 1a supernova were found to be reliable standard candles. This Hubble image shows the inner region of galaxy NGC 4319. The unusually dark, misshapen dust lanes in the galaxy's inner region are evidence of a disturbance probably caused by an early interaction with another galaxy. In 1994, NGC 3370 hosted a Type 1a supernova designated SN 1994 AE. The stellar outburst briefly outshone all of the tens of billions of other stars in its galaxy. Although supernovae are common, with one exploding every few seconds somewhere in the universe, this one was special. This supernova was one of the nearest and best observed since the advent of modern digital detectors. NGC 1309 is one of about 200 galaxies that make up the Eridanus galactic group. It was home to Type 1a supernova SN 2002FK. Its light reached Earth in September 2002. It also contains a number of Cepheid variables resolved by the Hubble Space Telescope. And, once again, the Type 1a was shown to be an excellent standard candle. NGC 7049 is the brightest of a cluster of galaxies called Brightest Cluster Galaxies, or BCG for short. Typical BCGs are some of the oldest and most massive galaxies. In 1923, after finding the D1 Cepheid variable in Andromeda and determining that Andromeda was an entire galaxy over 2 million light-years from our own, Hubble turned his sights on other spiral and elliptical nebula and found that they were galaxies as well. In his studies of these galaxies, he mapped their radial velocity as determined by the shift in spectral lines against their distance from us. He found what we see here in the Virgo supercluster. NGC 1068 is 35 million light-years away and receding at 784 kilometers per second. NGC 3949 is 50 million light-years away and receding at 1,120 kilometers per second. NGC 4414, a galaxy studied by the Key Project on extragalactic distance scales, is 62 million light-years away and receding at 1,336 kilometers per second. NGC 4319, a galaxy with both Cepheid variables and Type 1a supernova, is 80 million light-years away and receding at 1,792 kilometers per second. And NGC 1309, also a galaxy with both Cepheid variables and Type 1a supernova, is 100 million light-years away and receding at 2,244 kilometers per second. Hubble found that, except for a few nearby local group galaxies, all the spectra shifts were to the red. All the galaxies were moving away from us. And more than that, he found that the further away from us they are, the faster they are moving away from us. And even more than that, he found that the relationship between velocity and distance is linear. The graph is a straight line. The equation is simple. The receding velocity of a galaxy is equal to the slope of the line, a constant, times the distance the galaxy is away from us. Today that constant is known as the Hubble constant, and the equation is known as Hubble's law. If we measure the redshift of a galaxy, we can determine its receding velocity. And knowing its receding velocity, this equation tells us how far away it is. This gives us a new rung on our cosmic distance ladder called redshift. The accuracy of this rung depends entirely on the value of the Hubble constant. That's why it's one of the most studied numbers in astronomy and cosmology. This constant has been refined over time, and the distances used to see how far it holds has increased by orders of magnitude with our modern ability to determine distances with space telescopes like Hubble, analyzing Type 1a supernova out to billions of light-years. The box at the lower left shows the region of Hubble roamed. The current best value for the Hubble constant using this approach is 22.4 kilometers per second per million light-years, plus or minus 3.2. That's around 13 miles per second per million light-years. That is, a receding velocity of a galaxy goes up by 22.4 kilometers per second for each additional million light years away from us it is. This slow and steady movement of galaxies away from us is called the Hubble flow. This Hubble flow, where galaxies are getting further away with time, also implies that in the past they were closer together. It follows that we can ask, how long would it take a galaxy to reach its current distance from us, given its current velocity? That's simply the distance divided by the velocity, or 1 over the Hubble constant, 13.4 billion years. That's the age of the universe. We'll see later in our chapter on the cosmos that the Hubble constant turned out to not be constant over large enough times and distances. In modern cosmology, it is called the Hubble parameter, and it gives us a slightly larger age for the universe, around 13.8 billion years. Direct measurements, triangulation, and parallax took us across Earth, the solar system, and nearby stars. We added expansion parallax for planetary nebula and a number of powerful standard candles that were verified against stars that could be measured via parallax. This took us all the way across the Milky Way and into our local supercluster, Virgo. Here, Cepheid variables confirmed the accuracy of Type 1a supernova as an excellent standard candle. This is critical because even with the Hubble Space Telescope, we can't see Cepheid stars much further than 100 million light years. But we can see Type 1a supernova out to 8 billion light years. In addition, Cepheids and Type 1as have given us redshift as a way to tell distance. This rung is only limited by what is visible, and we'll see in later segments we can see out to around 13 billion light years. Here we have just seen a few of the galaxies in the vast Virgo supercluster. But Virgo is only one of millions of superclusters in the observable universe. In the next segment, we'll take a look at our local group of superclusters and introduce a new way to measure supercluster boundaries, with Laniakea being the one we are in.
Shall we go to the majestic and still mysterious view? Before you explain what's the explain,
Yes.
tell me what is the beauty of one single string?
Well, the idea in string theory is that elementary particles, instead of being point particles that obey quantum mechanical laws, are little loops of vibrating string that also obey quantum mechanical laws. And the beauty of that is that it describes many different things all at once. If you've got, for instance, a violin string or a piano string, they have many different modes or harmonics of vibration. If you pluck a string which is at middle C, for instance, you also see the higher harmonics. And that's responsible for the beauty of music. The reason we have symphony orchestras and not just tuning forks is that different instruments excite the higher harmonics in different amounts. The pure tone of the tuning fork sounds garish and ugly to the ear. The rich sound of a violin comes from the mixture of the different harmonics. Now in the case of the string, you've got this one vibrating string. It has many different harmonics, and we perceive those different harmonics as different elementary particles. So for instance, the electron, the quark, the photon, the neutrino, the graviton, all these things are different modes of vibration of a single string. And that's very beautiful and harmonious, getting the different particles from different forms of vibration of the string, just as a musician gets the richness of the tone from the harmonics of the violin string.
How small is a string? If I say small means in this case that the superstring is looks up at an atom, as an atom looks up to the entire solar system. Am I right?
Something like that. We don't understand exactly how small they are because we don't understand the theory perfectly. But roughly speaking, the proportion of the solar system to an atom is like the proportion of an atom to a string.
That's small.
That's pretty small. And it's very important that these strings obey quantum mechanical laws. Maybe I'll just take a moment at the blackboard to explain that point of view. So, classically, a point particle, as we discussed before, traces out an orbit in space, which is made a little bit fuzzy. And that fuzziness is extremely important and has a lot to do with how quantum mechanics was discovered. Mm-hmm. For instance, at the beginning of the century, when people discovered that there were atoms and there were electrons and there were atomic nuclei, they had the problem that if you've got, for instance, a proton with an electron orbiting it, and then you use Maxwell's equations, you discover that that electron should be emitting electromagnetic radiation and should spiral into the atom in an extremely short time, much faster than the twinkling of an eye. What turned out, though, is that the quantum mechanical fuzziness keeps the electron from spiraling in. The notion of spiraling in is a classical concept, and that fuzzy electron is smeared out quantum mechanically in such a way that it just can't fall in. So this cured a basic problem in the theory of electricity and gave us our modern theories of atoms, molecules, and all the microscopic things, which are based on this quantum mechanical uncertainty. In the case of gravity, there is a similar problem. If you have one body orbiting another, Einstein's theory says that gravitational radiation should be emitted. And again, you have this problem of an in-spiral. And you might think that quantum mechanical fuzziness would cure it, but in fact it doesn't. An additional source of fuzziness is needed. And you get that in string theory. In string theory, instead of a point particle, which as time evolves traces out a loop, at each time you've got a little string, and then at a later time it's maybe somewhere else. And as time evolves, this fits together into a smooth surface called the world volume or world sheet of the string. But I've kind of drawn a classical picture here. It's made fuzzy. It's hard to draw, but I won't really do so. But we've got a quantum mechanical string. So it's spread out in two different ways. One is that it's a little string instead of a point, and secondly, it's quantum mechanical. So they both have the effect of smearing out a little bit our familiar concepts and making what we know become a little bit fuzzy. And just this combination solves the problem for gravity the way the quantum mechanical fuzziness did for electricity. But it leads to a theory whose predictive power is much tighter. The arbitrariness that you've got in the standard theory is greatly reduced in the case of the string theory. And that enables you to make statements that don't have an analog in the usual context, like the fact that gravity is an inevitable consequence. Now, in talking a little bit about how particles interact, I'm not going to try to draw the quantum mechanical fuzziness. It's always there, but it would be too complicated to try to keep track of it. So we're just going to draw classical pictures. But now I want to say something that Feynman taught us, that you should think of these particles as they move along in space and time, sometimes breaking into two, and sometimes rejoining. So here, one particle broke into two at this moment, and two rejoined into one here. The overall process is that two came in from the past, and two went out to the future. So that was a scattering process, and Feynman taught us how to calculate quantum mechanical probability amplitudes for every such picture. Well, the thing about them is that everyone will agree that there were definite space-time events where something happened. One particle broke into two, or two particles joined into one. And those events are what you might call technically singularities in this graph. They're distinguished events. And standard quantum field theory needs special rules for what happens at those singularities, which is the basic limitation of its predictive power. Even after I tell you what the particles are, you don't know how they interact. Because to know how they interact, you would need to know how they're allowed to break and join. And that's a separate question. In string theory, the setup is a little bit different. Each of these particles is replaced by a little tube, which describes the history of a propagating string. And where a particle breaks into two discontinuously, a string can smoothly split apart into two strings. And then here's another one coming in. And then they go out. So now I've drawn a space-time picture of two strings coming in the past and two going out in the future. And the point of this picture is meant to be that it's all perfectly smooth. Unlike this one, which has two discrete events at which breaking or joining happened. So the result of that is that if you know what the string is, you also know how it interacts. You know what it's allowed to do. But if you know what the particles are, you still need a separate recipe for how it's allowed to behave. So that sort of is the germ of the fact that string theory is much more predictive than standard quantum field theory. You don't need to separately say what the objects are and how they behave. Once you've said what the objects are, how they behave is completely defined. The other thing is that technically you run into problems in standard quantum field theory when these interaction events coincide in space-time. That's where you meet infinities that people grappled with for decades. For example, Freeman Dyson was one of those who discovered the renormalization of quantum electrodynamics, where the problems for electricity were finally definitively tamed. But for gravity, that process doesn't work. That's why gravity doesn't work with standard quantum field theory. But when you go to the string, because there aren't these distinguished events, the traditional difficulties disappear. And so gravity becomes possible, and when you probe more deeply, it actually becomes necessary in the light of string theory.
If you write down an equation or a picture like that, the strings, what is the beauty? Write down an equation of string theory, which is dear to your heart. It's a kind of beauty. Explain what it's all about.
The Nambu-Goto action.
You're talking about duality, for instance? Or?
We might start here with something more elementary. The Nambu-Goto action is the basic principle that determines how these strings move in space-time. And it's a beautiful equation that also governs the behavior of a soap bubble in ordinary space. So if you've ever seen the oscillations of a soap bubble, and you've ever noticed that they can take curious and graceful shapes, that's one manifestation of what this equation does. But its other manifestation is that it describes what the strings are, but it therefore also describes at the same time how they're allowed to behave, what the interactions are, how one string can break into two, how strings can scatter, what reactions can occur, how atoms can form.
It's the most complete.
Well, it's not the most complete, but it does a lot.
Yeah.
And in standard quantum field theory, that means in pre-string physics, it has no analog. Over here, you need to write bits and pieces. You can write a very nice piece that goes back sort of to Euler, Lagrange, and Newton in different aspects. And it's analog, which many who've studied physics would meet as undergraduates probably. Looks like that. And it's fairly close analog of the Nambu-Goto formula. But it only describes a piece of the picture. And there's the rest of the truth, which is where the particles are interacting or breaking or joining or whatever they're doing, where things are happening rather than just particles propagating freely. You need additional laws, which can't be written down neatly in this form. It takes another language completely. So in going to string theory, you replace this one. This one sort of describes a rubber band. Well, analogy is a little bit misleading. This one describes the soap bubble in the sense that this one describes something of lower dimension. But when we go from here to here, well, just mathematically, in some ways it's richer, but in some ways it's quite similar. But the physics that it describes is much more harmonious. Because a formula like this one can never give a complete account of the particles. You need separate rules for how they behave, how they interact, what they're allowed to do. This sort of just says what they are. But this formula says what the strings are and also how they behave. And people dreamed for a long time in physics to have something like that, where you'd automatically know the interactions once you knew what the particles were. You could say that in gravity, Einstein offered that for the gravitational field. But in the rest of physics, that's generally been out of reach. Bits and pieces of it are achieved. Something like that is achieved for the W and Z bosons on the electromagnetic field in the standard model of particle physics. But for the rest of the particles, like the neutrino or the electron, you really have got to go to the string picture. Before you're able to say that knowing what it is, you also know what it can do.
Yeah, in this formula, you see what it is, and you see what it can do.
That's right.
It's not a standstill, it's the movement of the universe, so to say.
Yeah, it describes...
Too poetic, or...
Well, It's not too poetic, but it's not exactly the phrase I would use either.
Yeah.
What I'd say, it's of course hard to convey it with perfect accuracy, but what I would try to say is that in the string case, once you say what the strings are, what strings you're trying to describe, then their behavior is uniquely determined. Whereas for electrons, you sort of dial the knobs. You can say what's the mass of the electron, what's its electric charge, and so on. And the standard quantum field theories would still make sense for different values of those numbers. In the way I've explained it so far, the way I've said it is that if you know what the string is, then you also know what it does. And that's sort of because this picture here is smooth while this other one has those interaction events where breaking and joining happens. But that's kind of not a complete explanation. In the particle side, you've got quite a lot of freedom in saying what the particles are allowed to be. In the string side, it's severely restricted what kind of strings you can introduce. That's a long story that took a lot of work in the 70s, because finding that there are any possibilities for relativistic strings was extremely difficult and occupied literally dozens of papers. So people by the mid-80s had distilled it to the fact that there seemed to be 5 string theories that made sense. There were 5 candidates for what kind of string you could have. They differed by very general properties. For instance, in some theories, in some cases the string was an insulator. In other cases the strings were superconductors. In some cases the strings were closed loops like I drew on the blackboard. And in one of the 5 theories the strings were allowed to have endpoints, like pieces of string instead of closed loops. But anyway, when all is said and done, when you put in all the constraints of relativistic quantum mechanics, there were 5 kinds of strings you could do. So there seemed to be 5 candidates for how you could describe nature in this new framework. There was a period in the early 80s when it seemed that there was this very wonderful new framework for physics. There were 3 candidates, 2 hadn't yet been discovered. In this new framework, gravity was inevitable, while in the pre-string framework it was actually impossible. And that, of course, was very attractive and exciting. But on the other hand, you could also point to things that were wrong. These 3 theories were unified theories of gravity, quantum mechanics, and matter. But some aspects of the matter were wrong. What bothered me the most in those days was that you could argue in general that in any of those 3 theories, the weak interactions would have to conserve parity, which means that nature would look the same if you looked in a mirror. But we've known since the 50s that although nature almost looks the same if you look in the mirror, if you look very closely at the details of radioactive decays of certain atoms, you see that actually nature isn't symmetrical between left and right. If you take a movie and then you put the film in backwards and project it, most things in everyday life would look fine, but certain experiments in elementary particle physics and nuclear physics actually wouldn't make sense if the film was played backwards. Yet it seemed that you could prove in string theory that the theory would have to be symmetrical between left and right, at least for the realm of the standard experiments. That was wrong. That was a really important contradiction, I thought, between string theory and nature. And it motivated a lot of work that I and eventually others did in that period. In 1983, Alvarez Gomez and I did a calculation involving gravitational anomalies that made very precise why the weak interactions would have to be symmetrical between left and right. And then in 1984 there was the breakthrough that Green and Schwartz made, where they got a new insight about the anomaly cancellation. And suddenly the idea that the weak interactions had to be symmetrical between left and right was out the window. But then a lot of other things happened. So the weak interactions could break the symmetry, but then the models of elementary particle physics became a lot more realistic in very short order, especially with the discovery of the other 2 string theories, the heterotic strings. So this of course made a tremendous impression on me, because if the theory was wrong, the question you asked, well, how can you avoid left-right symmetry of the theory, might not have had an answer. And even if you could have conjured up some mathematical answer or not, nothing good would have necessarily come out of it. The fact that when you solve this problem, so many other things popped into place is the kind of thing which, in my judgment, doesn't happen if you're on the wrong track overall. So, since then, I personally haven't had doubts that it must be on the right track. You know, how many more layers we've got to peel away before we understand it is another story.
In what direction
But
do you
I don't
think
have-
if you say it will completely change our way of thinking about nature, the laws of nature?
Well, you see, somehow space and time will only be approximations. I don't know exactly how, but very, very roughly, the classical idea of position and velocity of a particle is an approximation in quantum mechanics that you get when you can treat certain operators as if they commute. If you don't care which of two things is done first, then you can talk about the classical ideas. But if you pay attention to what's first and what's last, then you're in this quantum mechanical world where everything is much stranger. Now, in the framework of physics that we have up till now, position and velocity have been confounded, but space and time still are perfectly sharp. But it's very clear for a lot of reasons that in the future, the concepts of space and time are going to be fuzzed up. That there will be something new that we've got that's more basic than space and time as we know them. And space and time will be approximations that will make sense when the lengths and times involved are big. When the lengths and times involved are small, they won't make sense. That's why the very notion of time will break down near the Big Bang. If you want to understand the Big Bang, or black holes, or the structure of elementary particles, there's some deeper level about what space and time really are, which is what string theorists are grappling towards. The laws of nature, as they've been uncovered in the last few centuries, and especially as they've been uncovered in the last century, are very surprising. They're very subtle in the concepts that physicists have needed, and many of the details are surprising. We've mentioned some of them, like curvature of space-time, others that are equally surprising, like antimatter, the fact that every particle has a similar but opposite antiparticle, and they can annihilate when they meet, or conversely, they can be created from pure energy. There are lots and lots of surprising things. Here, in that case, I'm mentioning a surprising phenomenon, but the concepts by which the human mind explains or predicts them are also, in many cases, very surprising, very different from what you might notice just naively in everyday life in looking at things around you. They've got a great beauty, which is a little hard to describe, maybe, if one hasn't experienced it. It's an aesthetic beauty. They're the laws as we know them are very beautiful mathematically. They involve very interesting and subtle concepts.
Yeah, what do you mean by subtle?
Subtle? Well, it's very delicate, you see. If I gave you the naive idea, which is still on the blackboard, replace a definite orbit of a point particle by something fuzzy, you could think about it 1,000 people locked in a room for 1,000 years. And you might never come up with something as crazy as the actual answer, which involves quantum mechanical Hilbert spaces, operators that don't commute, wave functions that obey strange equations and have peculiar physical interpretations. So it's a rich story and it all hangs together beautifully and resolves many contradictions or apparent contradictions in nature that at first sight look just as strange as the question, what was there before the beginning? So lots of things that prove to have their explanations in strange mathematical structures that are relevant to nature seem paradoxical, just like some of the paradoxes about the beginning of time. So I think perhaps some viewers of this program might be accustomed to thinking about the beauty of music, for instance. But the beauty of science, and I might say also the beauty of pure mathematics, are very different, but they're just as real and vivid to those who experience them as the beauty of music. It's not just that in the course of time, physicists learned to write more and more accurate equations. In writing more and more accurate equations, physicists learned that the more and more accurate equations are based on new, subtle, and surprising concepts that fit together just right, resolve all the contradictions, do everything they have to do, whether it's going back to Newton's laws in the regime where Newton was able to study nature, or reproducing atomic behavior in certain other regimes. It fits together perfectly in ways that are really extremely surprising. And of course, the greatest thing about it is that it works.
Yeah.
It not just fits together logically, but it describes the world we live in. The best equations and the best theories we've got, as I've mentioned, are really quantum mechanics and general relativity. And the best theories are tested in so many different ways and apply so nicely to so many different phenomena that they really have remarkable power in describing nature. But one thing I'm trying to convey is that the thrill is not just from the power of being able to describe many things, but the combination of the beauty of the theory, the beauty or harmony of the theory, and its power in application to the real world. That combination gives a thrill that I think neither ingredient would fully give separately.
Curiosities of the Sky by Garrett Serviss. Preface. What Froude says of history is true also of astronomy. It is the most impressive where it transcends explanation. It is not the mathematics of astronomy, but the wonder and the mystery that seize upon the imagination. The calculation of an eclipse owes all its prestige to the sublimity of its data. The operation in itself requires no more mental effort than the preparation of a railway timetable. The dominion which astronomy has always held over the minds of men is akin to that of poetry. When the former becomes merely instructive and the latter purely didactic, both lose their power over the imagination. Astronomy is known as the oldest of the sciences, and it will be the longest lived, because it will always have arcana that have not been penetrated. Some of the things described in this book are little known to the average reader, while others are well known, but all possess the fascination of whatever is strange, marvelous, obscure, or mysterious, magnified, in this case by the pretentious scale of the phenomena. The idea of the author is to tell about these things in plain language, but with as much scientific accuracy as plain language will permit, showing the wonder that is in them without getting away from the facts. Most of them have hitherto been discussed only in technical form, and in treatises that the general public seldom sees and never reads. Among the topics touched upon are the strange unfixedness of the fixed stars, the vast migrations of the suns and worlds constituting the universe, the slow passing out of the existence of those collocations of stars which for thousands of years have formed famous constellations, preserving the memory of the mythological heroes and heroines, and perhaps of otherwise unrecorded history, the tendency of stars to assemble in immense clouds, swarms, and clusters, the existence in some of the richest regions of the universe of absolutely black, starless gaps, deeps, or holes, as if one were looking out of a window into the murkiest night, the marvelous phenomena of new or temporary stars, which appear as suddenly as conflagrations, and often turn into something else as eccentric as themselves, the amazing forms of the whirlpool, spiral, pinwheel, and lace or tress nebulae, the strange surroundings of the sun, only seen in particular circumstances, but evidently playing a constant part in the daily phenomena of the solar system, the mystery of the zodiacal light, and the Gegenschein, the extraordinary transformations undergone by comets and their tails, the prodigies of meteorites and masses of stone and metal fallen from the sky, the cataclysms that have wrecked the moon, the problem of life and intelligence on the planet Mars, the problematical origin and fate of the asteroids, the strange phenomena of the auroral lights. An attempt has been made to develop these topics in an orderly way, showing their connection so that the reader may obtain a broad general view of the chief mysteries and problems of astronomy, and an idea of the immense field of discovery which still lies, almost unexplored, before it. End of the preface.
Chapter 1. The Windows of Absolute Night. To most minds, mystery is more fascinating than science. But when science itself leads straight up to the borders of mystery, and there comes to a dead stop, saying, At present I can no longer see my way. The force of the charm is redoubled. On the other hand, the illimitable is no less potent in mystery than the invisible, whence the dramatic effect of Keith's stout Cortez staring at the boundless Pacific while all his men look at each other with a wild surmise, silent upon a peak in daring. It is with similar feelings that the astronomer regards certain places where, from the peaks of the universe, his vision seems to range out into endless empty space. He sees there the shore of his little isthmus, and beyond, unexplored immensity. The name coal sacks, given to these strange voids, is hardly descriptive. Rather, they produce upon the mind the effect of blank windows in a lonely house on a pitch-dark night, which, when looked at from the brilliant interior, become appalling in their rayless murk. Infinity seems to acquire a new meaning in the presence of these black openings in the sky, for as one continues to gaze, it loses its purely metaphysical quality and becomes a kind of entity, like the ocean. The observer is conscious that he can actually see the beginning of its ebon depths, in which the visible universe appears to float like an enchanted island, resplendent within with lights and life and gorgeous spectacles, and encircled with screens of crowded stars, but with its dazzling vistas ending at the fathomless sea of pure darkness which encloses all. The galaxy, or Milky Way, surrounds the borders of our island in space like a stellar garland, and when openings appear in it, they are, by contrast, far more impressive than the general darkness of the interstellar expanse seen in other directions. Yet even that expanse is not everywhere equally dark, for it contains gloomy deeps, discernible with careful watching. Here, too, contrast plays an important part, though less striking than within the galactic region. Some of Sir William Herschel's observations appear to indicate an association between these tenebrious spots and neighboring star clouds and nebula. It is an illuminating bit of astronomical history that when he was sweeping the then virgin heavens with his great telescopes, he was accustomed to say to his sister, who, notebook in hand, waited at his side to take down his words, fresh with the inspiration of discovery: "Prepare to write. The nebula are coming. Here space is vacant." The most famous of the coal sacks, and the first to be brought to general attention before astronomers had awakened to the significance of such things, lies adjacent to the Southern Cross, and is truly an amazing phenomenon. It is not alone the conspicuousness of this celestial vacancy, opening suddenly in the midst of one of the richest parts of the galaxy, that has given it its fame, but quite as much the superstitious awe with which it was regarded by the early explorers of the South Seas. To them, as well as to those who listened in rapt wonder to their tales, the coal sacks seemed to possess some occult connection with the mystic cross. In the eyes of the sailors it was not a vacancy so much as a sable reality in the sky, and as, shuddering, they stared at it, they piously crossed themselves. It was another of the magical wonders of the unknown South, and as such it formed the basis of many a wild surmise and many a sea dog's yarn. Scientific investigation has not diminished its prestige, and today no traveler in the southern hemisphere is indifferent to its fascinating strangeness, while some find it the most impressive spectacle of the Antarctic heavens. All around, up to the very edge of the yawning gap, the sheen of the Milky Way is surpassingly glorious, but there, as if in obedience to an almighty edict, everything vanishes. A single faint star is visible within the opening, producing a curious effect upon the sensitive spectator, like the sight of a tiny islet in the midst of a black, motionless, waveless tarn. The dimensions of the lagoon of darkness, which is oval or pear-shaped, are 8 degrees by 5, so that it occupies a space in the sky about 130 times greater than the area of the full moon. It attracts attention as soon as the eye is directed toward the quarter where it exists, and, by virtue of the rarity of such phenomena, it appears a far greater wonder than the drifts of stars that are heaped around it. Now that observatories are multiplying in the southern hemisphere, the great austral coal sack will, no doubt, receive attention proportioned to its importance as one of the most significant features of the sky. Already at the Sydney Observatory, photographs have shown that the southern portion of this dead sea of space is not quite bottomless, although its northern part defies the longest sounding lines of the astronomer. There is a similar but less perfect coal sack in the northern hemisphere, in the constellation of the Swan, which, strange to say, also contains a well-marked figure of a cross outlined by stars. This gap lies near the top of the cross-shaped figure. It is best seen by averted vision, which brings out the contrast with the Milky Way, which is quite brilliant around it. It does not, however, exercise the same weird attraction upon the eye as the southern coal sack, for instead of looking like an absolute void in the sky, it rather appears as if a canopy of dark gauze had been drawn over the stars. We shall see the possible significance of this appearance later. Just above the southern horizon of our northern middle latitudes, in summer, where the Milky Way breaks up into vast sheets of nebulous luminosity, lying over and between the constellations Scorpio and Sagittarius, there is a remarkable assemblage of coal sacks, though none is of great size. One of them, near a conspicuous star cluster in Scorpio, M80, is interesting for having been the first of these strange objects noted by Herschel. Probably it was its nearness to M80 which suggests to his mind the apparent connection of such vacancies with star clusters which we have already mentioned. But the most marvelous of the coal sacks are those that have been found by photography in Sagittarius. One of Bernard's earliest and most excellent photographs includes two of them, both in the star cluster M8. The larger, which is roughly rectangular in outline, contains one little star, and its smaller neighbor is lune-shaped, surely a most singular form for such an object. Both are associated with curious dark lanes running through the clustered stars like trails in the woods. Along the borders of these lanes the stars are ranked in parallel rows, and what may be called the bottoms of the lanes are not entirely dark, but pebbled with faint stellar points. One of them, which skirts the two dark gaps and traverses the cluster along its greatest diameter, is edged with lines of stars, recalling the alignment of the trees bordering a French highway. This road of stars cannot be less than many billions of miles in length. All about the cluster, the bed of the galaxy is strangely disturbed, and in places nearly denuded, as if its contents had been raked away to form the immense stack and the smaller accumulations of stars around it. The well-known Trifid Nebula is also included in the field of the photograph, which covers a truly marvelous region, so intricate in its mingling of nebula, star clusters, star swarms, star streams, and dark vacancies that no description can do it justice. Yet, chaotic as it appears, there is an unmistakable suggestion of unity about it, impressing the beholder with the idea that all the different parts are in some way connected and have not been fortuitously thrown together. Miss Agnes M. Clerk made the striking remark that the dusky lanes in M8 are exemplified on the largest scale in the great rift dividing the Milky Way from Cygnus in the northern hemisphere all the way to the Cross in the southern. Similar lanes are found in many other clusters, and they are generally associated with flanking rows of stars, resembling in their arrangement the thick-set houses and villas along the roadways that traverse the approaches to a great city. But to return to the black gaps. Are they really windows in the star walls of the universe? Some of them look rather as if they had been made by a shell fired through a luminous target, allowing the eye to range through the hole into the void space beyond. If science is discreetly silent about these things, what can the more venturesome and less responsible imagination suggest? Would a huge runaway sun, like Arcturus for instance, make such an opening if it should pass like a projectile through the Milky Way? It is at least a stimulating inquiry. Being probably many thousands of times more massive than the galactic stars, such a stellar missile would not be stopped by them, though its direction of flight might be altered. It would drag the small stars lying close to its course out of their spheres, but the ultimate tendency of its attraction would be to sweep them around in its wake, thus producing rather a star swarm than a vacancy. Those that were very close to it might be swept away in its rush and become its satellites, careering away with it in its flight into outer space. But those that were farther off, and they would, of course, greatly outnumber the nearer ones, would tend inward from all sides toward the line of flight, as dust and leaves collect behind a speeding motor, though the forces operating would be different, and would fill up the hole, if hole it were. A swarm thus collected should be rounded in outline and bordered with a relatively barren ring from which the stars had been sucked away. In a general sense, the M8 cluster answers to this description, but even if we undertook to account for its existence by a supposition like the above, the black gaps would remain unexplained unless one could make a further draft from the imagination and suggest that the stars had been thrown into a vast eddy or system of eddies whose vortices appear as dark holes. Only a maelstrom-like motion could keep such a funnel open, for, without regard to the impulse derived from the projectile, the proper motions of the stars themselves would tend to fill it. Perhaps some other cause of the whirling motion may be found. As we shall see when we come to the spiral nebula, gyratory movements are exceedingly prevalent throughout the universe, and the structure of the Milky Way is everywhere suggestive of them. But this is hazardous sport, even for the imagination, to play with suns as if they were but thistledown in the wind or quartz in a mill race. Another question arises. What is the thickness of the hedge of stars through which the holes penetrate? Is the depth of the openings proportionate to their width? In other words, is the Milky Way round in section like a rope, or flat and thin like a ribbon? The answer is not obvious, for we have little or no information concerning the relative distances of the faint galactic stars. It would be easier, certainly, to conceive of openings in a thin belt than in a massive ring, for in the first case they would resemble mere rifts and breaks, while in the second they would be like wells or boreholes. Then, too, the fact that the Milky Way is not a continuous body, but is made up of stars whose actual distances apart is great, offers another quantity. Persistent and sharply bordered apertures in such an assemblage are a priori as improbable, if not impossible, as straight, narrow holes running through a swarm of bees. The difficulty of these questions indicates one of the reasons why it has been suggested that the seeming gaps, or many of them, are not openings at all, but opaque screens cutting off the light from stars behind them. That this is quite possible in some cases is shown by Bernard's later photographs, particularly those of the singular region around the star Rho Ophiuchi. Here are to be seen somber lanes and patches, apparently forming a connected system which covers an immense space, and which their discoverer thinks may constitute a dark nebula. This seems at first a startling suggestion, but, after all, why should there not be dark nebula as well as visible ones? In truth, it has troubled some astronomers to explain the luminosity of the bright nebula, since it is not to be supposed that matter in so diffuse a state can be incandescent through heat, and phosphorescent light is in itself a mystery. The supposition is also in accord with what we know of the existence of dark, solid bodies in space. Many bright stars are accompanied by obscure companions, sometimes as massive as themselves. The planets are non-luminous. The same is true of meteors before they plunge into the atmosphere and become heated by friction, and many plausible reasons have been found for believing that space contains as many obscure as shining bodies of great size. It is not so difficult, after all, then, to believe that there are immense collections of shadowy gases and meteoric dust whose presence is only manifested when they intercept the light coming from shining bodies behind them. This would account for the apparent extinguishment of light in open space, which is indicated by the falling off in relative number of telescopic stars below the 10th magnitude. Even as things are, the amount of light coming to us from stars too faint to be seen with the naked eye is so great that the statement of it generally surprises persons who are unfamiliar with the inner facts of astronomy. It has been calculated that on a clear night, the total starlight from the entire celestial sphere amounts to 1/60th of the light of the full moon. But of this, less than 1/25th is due to stars separately distinguished by the eye. If there were no obscuring medium in space, it is probable that the amount of starlight would be noticeably and perhaps enormously increased. But while it seems certain that some of the obscure spots in the Milky Way are due to the presence of dark nebula, or concealing veils of one kind or another, it is equally certain that there are many which are true apertures, however they may have been formed, and by whatever forces they may be maintained. These, then, are veritable windows of the galaxy, and when looking out of them, one is face to face with the great mystery of infinite space. There, the known universe visibly ends, but manifestly space itself does not end there. It is not within the power of thought to conceive an endless space. For the instant we think of a terminal point or line, the mind leaps forward to the beyond. There must be space outside as well as inside. Eternity of time and infinity of space are ideas that the intellect cannot fully grasp. But neither can it grasp the idea of a limitation to either space or time. The metaphysical conceptions of hypergeometry, or fourth-dimensional space, do not aid us. Having, then, discovered that the universe is a thing contained in something indefinitely greater than itself, having looked out of its windows and found only the gloom of starless night outside, what conclusions are we to draw concerning the beyond? It seems as empty as a vacuum, but is it really so? If it be, then our universe is a single atom astray in the infinite. It is the only island in an ocean without shores. It is the one oasis in an illimitable desert. Then the Milky Way, with its wide-flung garland of stars, is afloat like a tiny smoke wreath amid a horror of immeasurable vacancy. Or it is an evanescent and solitary ring of sparkling froth cast up for a moment on the viewless billows of immensity. From such conclusions the mind instinctively shrinks. It prefers to think that there is something beyond, though we cannot see it. Even the universe could not bear to be alone, a Crusoe lost in the cosmos. As the inhabitants of the most elegant chateau, with its gardens, peaks, and crowds of attendants, would die of loneliness if they did not know that they have neighbors, though not seen, and that a living world of indefinite extent surrounds them. So we, when we perceive that the universe has limits, wish to feel that it is not solitary, that beyond the hedges and the hills there are other centers of life and activity. Could anything be more terrible than the thought of an isolated universe? The greater the being, the greater the aversion to seclusion. Only the infinite satisfies. In that alone the mind finds rest. We are driven then to believe that the universal night which envelops us is not tenantless, that as we stare out of the star-framed windows of the galaxy and see nothing but uniform blackness, the fault is with our eyes or is due to an obscuring medium. Since our universe is limited in extent, there must be other universes beyond it on all sides. Perhaps if we could carry our telescopes to the verge of the great pole stack near the cross, being then on the frontier of our starry system, we could discern, sparkling afar off in the vast night, some of the outer galaxies. They may be grander than ours, just as many of the suns surrounding us are immensely greater than ours. If we could take our stand somewhere in the midst of immensity and, with vision of infinite reach, look about us, we should perhaps see a countless number of stellar systems, amid which ours would be unnoticeable, like a single star among the multitude glittering in the terrestrial sky on its way. Some might be in the form of a reef, like our own. Some might be globular, like the great star clusters in Hercules and Centaurus. Some might be glittering circles, or disks, or rings within rings. If we could enter them, we should probably find a vast variety of compositions, including elements unknown to terrestrial chemistry. For while the visible universe appears to contain few, if any, substances not existing on the Earth or in the Sun, we have no warrant to assume that others may not exist in infinite space. And how as to gravitation? We do not know that gravitation acts beyond the visible universe, but it is reasonable to suppose that it does. At any rate, if we let go its sustaining hand, we are lost, and can only wander hopelessly in our speculations, like children astray. If the empire of gravitation is infinite, then the various outer systems must have some, though measuring by our standards an imperceptible, attractive influence upon each other. For gravitation never lets go its hold, however great the space over which it is required to act. Just as the stars about us are all in motion, so the starry systems beyond our sight may be in motion, and our system as a whole may be moving in concert with them. If this be so, then after interminable ages, the aspect of the entire system of systems must change, its various members assuming new positions with respect to one another. In the course of time, we may even suppose that our universe will approach relatively close to one of the others. And then, if men are yet living on the Earth, they may glimpse through the openings which reveal nothing to us now the lights of another nearing star system, like the signals of a strange squadron, bringing them the assurance, which can be but an inference at present, that the ocean of space has other argosies venturing on its limitless expanse. There remains the question of the luminiferous ether by whose agency the waves of light are borne through space. The ether is as mysterious as gravitation. With regard to ether, we only infer its existence from the effects which we ascribe to it. Evidently, the ether must extend as far as the most distant visible stars. But does it continue on indefinitely in outer space? If it does, then the invisibility of other systems must be due to their distance, diminishing the quantity of light that comes from them below the limit of perceptibility, or to the interposition of absorbing media. If it does not, then the reason why we cannot see them is owing to the absence of a means of conveyance for the light waves, as the lack of an interplanetary atmosphere prevents us from hearing the thunder of sunspots. It is interesting to recall that Mr. Edison was once credited with the intention to construct a gigantic microphone, which should render the roar of sunspots audible by transforming the electric vibrations into sound waves. On this supposition, each starry system would be enveloped in its own globule of ether, and no light could cross from one to another. But the probability is that both the ether and gravitation are ubiquitous, and that all the stellar systems are immersed in the former like clouds of phosphorescent organisms in the sea. So astronomy carries the mind from height to greater height. Men were long in accepting the truth of the relative insignificance of the Earth. They were more quickly convinced of the comparative littleness of the solar system, and now the evidence assails their reason that what they had regarded as the universe is only one mote gleaming in the sunbeams of infinity. End of Chapter 1. Chapter 2. Star clouds, star clusters, and star streams. In the preceding chapter, we have seen something of the strangely complicated structure of the galaxy, or Milky Way. We now proceed to study more comprehensively that garlanded pathway of the gods. Judged by the eye alone, the Milky Way is one of the most delicately beautiful phenomena in the entire realm of nature. A shimmer of silvery gauze stretched across the sky. But studied in the light of its revelations, it is the most stupendous object presented to human ken. Let us consider, first, its appearance to ordinary vision. Its apparent position in the sky shifts according to the season. On a serene, cloudless summer evening, in the absence of the moon, whose light obscures it, one sees the galaxy spanning the heavens from north to southeast of the zenith like a phosphorescent arch. In early spring, it forms a similar, but upon the whole less brilliant arch west of the zenith. Between spring and summer, it lies like a long, faint twilight band along the northern horizon. At the beginning of winter, it again forms an arch, this time spanning the sky from east to west, a little north of the zenith. These are its positions as viewed from the mean latitude of the United States. Even the beginner in stargazing does not have to watch it throughout the year in order to be convinced that it is in reality a great circle extending entirely around the celestial sphere. We appear to be situated near its center, but its periphery is evidently far away in the depths of space. Although to the casual observer it seems but a delicate scarf of light, brighter in some places than in others, but hazy and indefinite at the best. Such is not its appearance to those who study it with care. They perceive that it is an organic whole, though marvelously complex in detail. The telescope shows that it consists of stars too faint and small through excess of distance to be separately visible. Of the 100 million suns which some estimates have fixed as the probable population of the starry universe, the vast majority, at least 30 to 1, are included in this strange belt of misty light, but they are not uniformly distributed in it. On the contrary, they are arrayed in clusters, knots, bunches, clouds, and streams. The appearance is somewhat as if the galaxy consisted of innumerable swarms of silver-winged bees, more or less intermixed, some massed together, some crossing the paths of others, but all governed by a single purpose which leads them to encircle the region of space in which we are situated. From the beginning of the systematic study of the heavens, the fact has been recognized that the form of the Milky Way denotes the scheme of the sidereal system. At first it was thought that the shape of the system was that of a vast round disk, flat like a cheese, and filled with stars, our sun and his relatively few neighbors being placed near the center. According to this view, the galactic belt was an effective perspective, for when looking in the direction of the plane of the disk, the eye ranged through an immense extension of stars which blended into a glimmering blur, surrounding us like a ring, while when looking out from the sides of the disk, we saw but few stars, and in those directions the heavens appeared relatively blank. Finally, it was recognized that this theory did not correspond with the observed appearances, and it became evident that the Milky Way was not a mere effective perspective, but an actual band of enormously distant stars, forming a circle about the sphere, the central opening of the ring, containing many scattered stars, being many times broader than the width of the ring itself. Our Sun is one of the scattered stars in the central opening. As already remarked, the ring of the galaxy is very irregular, and in places it is partly broken. With its sinuous outline, its pendant sprays, its graceful and accordant curves, its bunching of masses, its occasional interstices, and the manifest order of a general plan governing the jumble of its details, it bears a remarkable resemblance to a garland, a fact which appears the more wonderful when we recall its composition. That an elm tree should trace the lines of beauty with its leafy and pendulous branches does not surprise us, but we can only gaze with growing amazement when we behold 100 million suns imitating the form of a chaplet, and then we have to remember that this form furnishes the ground plan of the universe. As an indication of the extraordinary speculations to which the mystery of the Milky Way has given rise, a theory recently, 1909, proposed by Professor George C. Comstock may be mentioned. Starting with the data, first, that the number of stars increases as the Milky Way is approached and reaches a maximum in its plane, while on the other hand, the number of nebulae is greatest outside the Milky Way and increases with distance from it, and second, that the Milky Way, although a complete ring, is broad and diffuse on one side through one half its course, that half alone containing nebulae, and relatively narrow and well defined on the opposite side. The author of this singular speculation avers that these facts can best be explained by supposing that the invisible universe consists of two interpenetrating parts, one of which is a chaos of indefinite extent, strewn with stars and nebulous dust, and the other a long, broad, but comparatively thin cluster of stars, including the Sun as one of its central members. This flat star cluster is conceived to be moving edgewise through the chaos, and, according to Professor Comstock, it acts after the manner of a snowplow sweeping away the cosmic dust and piling it on either hand above and below the plane of the moving cluster. It thus forms a transparent rift, through which we see farther and command a view of more stars than through the intensified dust clouds on either hand. This rift is the Milky Way. The dust thrown aside toward the poles of the Milky Way is the substance of the nebulae which are bound there. Ahead, where the front of the star plow is clearing the way, the chaos is nearer at hand, and consequently, there the rift subtends a broader angle, and is filled with primordial dust, which, having been annexed by the vanguard of the star swarm, forms a nebulae seen only in that part of the Milky Way. But behind, the rift appears narrow, because there we look farther away between the dust clouds produced ages ago by the front of the plow, and no scattered dust remains in that part of the rift. In quoting an outline of this strikingly original theory, the present writer should not be understood as assenting to it. That it appears bizarre is not in itself a reason for rejecting it, when we are dealing with so problematical and enigmatical a subject as the Milky Way, but the serious objection is that the theory does not sufficiently accord with the observed phenomena. There is too much evidence that the Milky Way is an organic system, however fantastic its form, to permit the belief that it can only be a rift in chaotic clouds. As with every organism, we find that its parts are more or less clearly repeated in its ensemble. Among all the strange things that the Milky Way contains, there is nothing so extraordinary as itself. Every astronomer must many times have found himself marveling at it in those comparatively rare nights when it shows all its beauty and all its strangeness. In its great broken rifts, divisions, and spirals are found the gigantic prototypes of similar forms in its star clouds and clusters. As we have said, it determines the general shape of the whole sidereal system. Some of the brightest stars in the sky appear to hang like jewels suspended at the ends of tassels dropped from the galaxy. Among these pendants are the Pleiades and the Hyades. Orion, too, the mighty hunter, is caught in a loop of light thrown out from it. The majority of the great first magnitude stars seem related to it, as if they formed an inner ring inclined at an angle of some 20 degrees to its plane. Many of the long curves that set off from it on both sides are accompanied by corresponding curves of lucid stars. In a word, it offers every appearance of structural connection with the entire starry system. That the universe should have assumed the form of a wreath is certainly a matter for astonishment. But it would have been still more astonishing if it had been a cube, a rhomboid, or a dodecahedron, for then we should have had to suppose that something resembling the forces that shape crystals had acted upon the stars, and the difficulty of explaining the universe by the laws of gravitation would have been increased. From the Milky Way as a whole, we pass to the vast clouds, swarms, and clusters of stars of which it is made up. It may be, as some astronomers hold, that most of the galactic stars are much smaller than the Sun, so that their faintness is not due entirely to the effect of distance. Still, their intrinsic brilliance attests to their solar character, and considering their remoteness, which has been estimated at not less than 10,000 to 20,000 light years, a light year is equal to nearly 6,000 million miles, their actual masses cannot be extremely small. The minutest of them are entitled to be regarded as real suns, and they vary enormously in magnitude. The effects of their attractions upon one another can only be inferred from their clustering, because their relative movements are not apparent on account of the brevity of the observations that we can make. But imagine a being for whom a million years would be but as a flitting moment. To him, the Milky Way would appear in a state of ceaseless agitation, swirling with a fury of whirlpool motion. The cloud-like aspect of large parts of the galaxy must always have attracted attention, even from naked-eye observers, but the true star clouds were first satisfactorily represented in Barnard's photographs. The resemblance to actual clouds is often startling. Some are close-packed and dense, like cumuli. Some are wispy or mottled, like cirri. The rifts and modulations, as well as the general outlines, are the same as those of clouds of vapor or dust, and one notices also the characteristic thinning out at the edges. But we must beware of supposing that the component suns are thickly crowded as the particles forming an ordinary cloud. They look, indeed, as if they were matted together because of the irradiation of light, but in reality, millions and billions of miles separate each star from its neighbors. Nevertheless, they form real assemblages, whose members are far more closely related to one another than is our Sun to the stars around him, and if we were in the Milky Way, the aspect of the nocturnal sky would be marvelously different from its present appearance. Stellar clouds are characteristic of the galaxy and are not found beyond its borders, except in the Magellanic clouds of the southern hemisphere, which resembles detached portions of the Milky Way. These singular objects form as striking a peculiarity of the austral heavens as does the great coal sack described in Chapter 1. But it is their isolation that makes them so remarkable, for their composition is essentially galactic, and if they were included within its boundaries, they would not appear more wonderful than many other parts of the Milky Way. Placed where they look like masses fallen from the great stellar arch. They are full of nebulae and star clusters, and show striking evidences of spiral movement. Star swarms, which are also characteristic features of the galaxy, differ from star clouds very much in the way that their name would imply. That is, their component stars are so arranged, even when they are countless in number, that the idea of an exceedingly numerous assemblage, rather than that of a cloud, is impressed on the observer's mind. In a star swarm, the separate members are distinguishable because they are either larger or nearer than the stars composing a cloud. A splendid example of a true star swarm is furnished by Chi Persei in that part of the Milky Way which runs between the constellations Perseus and Cassiopeia. This swarm is much coarser than many others and can be seen by the naked eye. In a small telescope it appears double, as if the suns composing it had divided into two parties which keep on their way side by side, with some commingling of their members where the skirts of the two companies come in contact. Smaller than either star clouds or star swarms, and differing from both in their organization, are star clusters. These, unlike the others, are found outside as well as inside the Milky Way, although they are more numerous inside its boundaries than elsewhere. The term star cluster is sometimes applied, though improperly, to assemblages which are rather groups, such, for instance, as the Pleiades. In their most characteristic aspect, star clusters are of a globular shape, globes of suns. A famous example of a globular star cluster, but one not included in the Milky Way, is the Great Cluster in Hercules. This is barely visible to the naked eye, but a small telescope shows its character, and in a large one it presents a marvelous spectacle. Photographs of such clusters are perhaps less effective than those of star clouds, because the central condensation of stars in them is so great that their light becomes blended in an undistinguishable blur. The beautiful effect of the incessant play of infinitesimal rays over the apparently compact surface of the cluster, as if it were a globe of the finest frosted silver shining in an electric beam, is also lost in a photograph. Still, even to the naked eye, looking directly at the cluster through a powerful telescope, the central part of the wonderful congregation seems almost a solid mass in which the stars are packed like the ice crystals in a snowball. The same question arises to the lips of every observer. How can they possibly have been brought into such a situation? The marvel does not grow less when we know that instead of being closely compacted, the stars of the cluster are probably separated by millions of miles. For we know that their distances apart are slight as compared with their remoteness from the Earth. Sir William Herschel estimated their number to be about 14,000, but in fact they are uncountable. If we could view them from a point just within the edge of the assemblage, they would offer the appearance of a hollow hemisphere emblazoned with stars of astonishing brilliancy, the nearby ones unparalleled in splendor by any celestial object known to us, while the more distant ones would resemble ordinary stars. An inhabitant of the cluster would not know, except by a process of ratiocination, that he was dwelling in a globular assemblage of suns. Only from a point far outside would their spherical arrangement become evident to the eye. Imagine 14,000 fire balloons with an approach to regularity in a spherical space, say 10 miles in diameter. There would be an average of less than 30 in every cubic mile, and it would be necessary to go to a considerable distance in order to see them as a globular aggregation. Yet from a point sufficiently far away, they would blend into a glowing ball. Photographs show even better than the best telescopic views that the great cluster is surrounded with a multitude of dispersed stars, suggestively arrayed in more or less curving lines, which radiate from the principal mass with which their connection is manifest. These stars, situated outside the central sphere, look somewhat like vagrant bees buzzing around a dense swarm where the queen bee is sitting. Yet, while there is so much to suggest the operation of central forces, bringing and keeping the members of the cluster together, the attentive observer is also impressed with the idea that the whole wonderful phenomenon may be the result of explosion. As soon as this thought seizes the mind, confirmation of it seems to be found in the appearance of the outlying stars, which could be as readily explained by the supposition that they have been blown apart as that they have flocked together toward a center. The probable fact that the stars constituting the cluster are very much smaller than our Sun might be regarded as favoring the hypothesis of an explosion. Of their real size we know nothing, but on the basis of an uncertain estimate of their parallax, it has been calculated that they may average 45,000 miles in diameter, something more than half the diameter of the planet Jupiter. Assuming the same mean density, 14,000 such stars might have been formed by the explosion of a body about twice the size of the Sun. This recalls the theory of Olbers, which has never been altogether abandoned or disproved, that the asteroids were formed by the explosion of a planet circulating between the orbits of Mars and Jupiter. The asteroids, whatever their manner of origin, form a ring around the Sun, but of course the explosion of a great independent body, not originally revolving about a superior center of gravitational force, would not result in the formation of a ring of small bodies, but rather of a dispersed mass of them. But back of any speculation of this kind lies the problem, at present insoluble. How could the explosion be produced? See the question of explosions in chapters 6 and 14. Then, on the other hand, we have the observation of Herschel, since abundantly confirmed, that space is unusually vacant in the immediate neighborhood of condensed star clusters and nebulae, which, as far as it goes, might be taken as an indication that the assembled stars had been drawn together by their mutual attractions, and that the tendency to aggregation is still bringing new members toward the cluster. But in that case, there must have been an original condensation of stars at that point in space. This could probably have been produced by the coagulation of a great nebula into stellar nuclei, a process which seems now to be taking place in the Orion Nebula. A yet more remarkable globular star cluster exists in the southern hemisphere, Omega Centauri. In this case, the central condensation of stars presents an almost uniform blaze of light. Like the Hercules cluster, that in Centaurus is surrounded with stars scattered over a broad field and showing an appearance of radial arrangement. In fact, except for its greater richness, Omega Centauri is an exact duplicate of its northern rival. Each appears to an imaginative spectator as a veritable city of suns. Mathematics shrinks from the task of disentangling the maze of motions in such an assemblage. It would seem that the chance of collisions is not to be neglected, and this idea finds a certain degree of confirmation in the appearance of temporary stars, which have more than once blazed out in, or close by, globular star clusters. This leads up to the notable fact, first established by Professor Bailey a few years ago, that such clusters are populous with variable stars. Omega Centauri and the Hercules cluster are especially remarkable in this respect. The variables found in them are all of short period, and the changes of light show a noteworthy tendency to uniformity. The first thought is that these phenomena must be due to collisions among the crowded stars, but if so, the encounters cannot be between the stars themselves, but probably between stars and meteor swarms revolving around them. Such periodic collisions might go on for ages without the meteors being exhausted by incorporation with the stars. This explanation appears all the more probable because one would naturally expect that flocks of meteors would abound in a close aggregation of stars. It is also consistent with Perrine's discovery that the globular star clusters are powdered with minute stars strewn thickly among the brighter ones. In speaking of Professor Comstock's extraordinary theory of the Milky Way, the fact was mentioned that, broadly speaking, the nebulae are less numerous in the galactic belt than in the comparatively open spaces on either side of it. but that they are, nevertheless, abundant in the broader half of the Milky Way, which he designates as the front of the gigantic plow supposed to be forcing its way through the enveloping chaos. In and around the Sagittarius region, the intermingling of nebulae and galactic star clouds and clusters is particularly remarkable. That there is a causal connection no thoughtful person can doubt. We are unable to get away from the evidence that a nebula is like a seed ground from which stars spring forth, or we may say that nebulae resemble clouds in whose bosom raindrops are forming. The wonderful aspect of the admixtures of nebulae and star clusters in Sagittarius has been described in Chapter 1. We now come to a still more extraordinary phenomenon of this kind, the Pleiades nebulae. The group of the Pleiades, although lying outside the main course of the galaxy, is connected with it by a faint loop, and is the scene of the most remarkable association of stars and nebulous matter known in the visible universe. The naked eye is unaware of the existence of nebulae in the Pleiades, or, at the best, merely suspects that there is something of the kind there, and even the most powerful telescopes are far from revealing the full wonder of the spectacle. But in photographs which have been exposed for many hours consecutively in order to accumulate the impression of the actinic rays, the revelation is stunning. The principal stars are seen surrounded by, and, as it were, drowned in, dense nebulous clouds of an unparalleled kind. The forms assumed by these clouds seem at first sight inexplicable. They look like fleeces, or perhaps more like splashes and daubs of luminous paint dashed carelessly from a brush. But closer inspection shows that they are to a large extent woven out of innumerable threads of filmy texture, and there are many indications of spiral tendencies. Each of the bright stars of the group, Alcyone, Merope, Maya, Electra, Taygeta, Atlas, is the focus of a dense fog, totally invisible, remember, alike to the naked eye and to the telescope, and these particular stars are veiled from sight behind the strange mists. Running in all directions across the relatively open spaces are nebulous wisps and streaks of the most curious forms. On some of the nebular lines, which are either straight throughout, or, if they change direction, do so at an angle, little stars are strung like beads. In one case, 7 or 8 stars are thus aligned, and, as if to emphasize their dependence upon the chain which connects them, when it makes a slight bend, the file of stars turns the same way. Many other star rows in the group suggest by their arrangements that they, too, were once strung upon similar threads which have now disappeared, leaving the stars spaced along their ancient tracks. We seem forced to the conclusion that there was a time when the Pleiades were embedded in a vast nebula resembling that of Orion, and that the cloud has now become so rare by gradual condensation into stars that the merest trace of it remains. And this would probably have escaped detection but for the remarkable actinic power of the radiant matter of which it consists. The richness of many of these faint nebulous masses in ultraviolet radiations, which are those that specifically affect the photographic plate, is the cause of the marvelous revelatory power of celestial photography. So the veritable unseen universe, as distinguished from the unseen universe of metaphysical speculation, is shown to us. A different kind of association between stars and nebulae is shown in some surprising photographic objects in the constellation Cygnus, where long, wispy nebulae, billions of miles in length, some of them looking like tresses streaming in a breeze, lie amid fields of stars which seem related to them. But the relation is of a most singular kind, for notwithstanding the delicate structure of the long nebulae, they appear to act as barriers, causing the stars to heap themselves on one side. The stars are 2, 3, or 4 times as numerous on one side of the nebulae as on the other. These nebulae, as far as appearance goes, might be likened to rail fences or thin hedges against which the wind is driving drifts of powdery snow, which, while scattered plentifully all around, tends to bank itself on the leeward side of the obstruction. The imagination is at a loss to account for these extraordinary phenomena, yet there they are, faithfully giving us their images whenever the photographic plate is exposed to their radiations. Thus, the more we see of the universe with improved methods of observation, and the more we invent aids to human senses, each enabling us to penetrate a little deeper into the unseen, the greater becomes the mystery. The telescope carried us far. Photography is carrying us still farther. But what as yet unimagined instrument will take us to the bottom, the top, and the end? And then, what hitherto untried power of thought will enable us to comprehend the meaning of it all? End of Chapter 2.
Chapter 3, Stellar Migrations. To the untrained eye, the stars and the planets are not distinguishable. It is customary to call them all alike stars. But since the planets more or less rapidly change their places in the sky, the consequence of their revolution about the sun, while the stars proper seem to remain always in the same relative positions, the latter are spoken of as fixed stars. In the beginnings of astronomy, it was not known that the fixed stars had any motion independent of their apparent annual revolution with the whole sky about the earth as a seeming center. Now, however, we know that the term fixed stars is paradoxical, for there is not a single really fixed object in the whole celestial sphere. The apparent fixity of the positions of the stars is due to their immense distance, combined with the shortness of time during which we are able to observe them. It is like viewing the plume of smoke issuing from a steamer, hull down at sea. If one does not continue to watch it for a long time, it appears to be motionless, although in reality it may be traveling at great speed across the line of sight. Even the planets seem fixed in position if one watches them for a single night only, and the more distant ones do not sensibly change their places, except after many nights of observation. Neptune, for instance, moves but little more than 2 degrees in the course of an entire year, and in a month its change of place is only about 1/3 of the diameter of the full moon. Yet, fixed as they seem, the stars are actually moving with a speed in comparison with which, in some cases, the planets might almost seem to be said to stand fast in their tracks. Jupiter's speed in its orbit is about 8 miles per second. Neptune's is less than 3½ miles, and the Earth's is about 18½ miles. While there are fixed stars which move 200 or 300 miles per second, they do not all, however, move with so great a velocity, for some appear to travel no faster than the planets. But in all cases, notwithstanding their real speed, long continued and exceedingly careful observations are required to demonstrate that they are moving at all. No more overwhelming impression of the frightful depths of space in which the stars are buried can be obtained than by reflecting upon the fact that a star whose actual motion across the line of sight amounts to 200 miles per second does not change its apparent place in the sky in the course of 1,000 years sufficiently to be noticed by the casual observer of the heavens. There is one vast difference between the motions of the stars and those of the planets to which attention should be at once called. The planets, being under the control of a central force emanating from their immediate master, the sun, all move in the same direction and in orbits concentric about the sun. The stars, on the other hand, move in every conceivable direction and have no apparent center of motion, for all efforts to discover such a center have failed. At one time, when theology had finally to accept the facts of science, a grandiose conception arose in some pious minds, according to which the throne of God was situated at the exact center of his creation, and, seated there, he watched the magnificent spectacle of the starry systems obediently revolving around him. Astronomical discoveries and speculations seemed for a time to afford some warrant for this view, which was, moreover, an acceptable substitute for the abandoned geocentric theory in mind that could only conceive of God as a superhuman artificer, constantly admiring his own work. No longer ago than the middle of the 19th century, a German astronomer, Maedler, believed he had actually found the location of the center about which the stellar universe revolved. He placed it in the group of the Pleiades, and upon his authority, an extraordinary imaginative picture was sometimes drawn of the star Alcyone, the brightest of all the Pleiades, as the very seat of the Almighty. This idea even seems to gain a kind of traditional support from the mystic significance, without known historical origin, which has for many ages, and among widely separated peoples, been attached to the remarkable group of which Alcyone is the chief. But since Maedler's time, it has been demonstrated that the Pleiades cannot be the center of revolution of the universe, and, as already remarked, all attempts to find or fix such a center have proved abortive. Yet, so powerful was the hold that the theory took upon the popular imagination that even today some astronomers are often asked if Alcyone is not the probable site of Jerusalem the Golden. If there were a discoverable center of predominant gravitative power to which the motions of all the stars could be referred, those motions would appear less mysterious, and we should then be able to conclude that the universe was, as a whole, a prototype of the subsidiary systems of which it is composed. We should look simply to the law of gravitation for an explanation, and naturally, the center would be placed within the opening enclosed by the Milky Way. If it were there, the Milky Way itself should exhibit signs of revolution about it, like a wheel turning upon its hub. No theory of the star motions as a whole could stand which failed to take account of the Milky Way as the basis of all. But the very form of that divided wreath of stars forbids the assumption of its revolution about a center. Even if it could be conceived as a wheel having no material center, it would not have the form which it actually presents. As was shown in Chapter 2, there is abundant evidence of motion in the Milky Way. But it is not motion of the system as a whole, but motion affecting its separate parts. Instead of all moving one way, the galactic stars, as far as their movements can be inferred, are governed by local influences and conditions. They appear to travel crosswise and in contrary directions, and perhaps they eddy around foci where great numbers have assembled, but of a universal revolution involving the entire mass, we have no evidence. Most of our knowledge of star motions, called proper motions, relates to individual stars and to a few groups which happen to be so near that the effects of their movements are measurable. In some cases, the motion is so rapid, not in appearance, but in reality, that the chief difficulty is to imagine how it can have been imparted, and what will eventually become of the runaways. Without a collision or a series of very close approaches to great gravitational centers, a star traveling through space at the rate of 200 or 300 miles per second could not be arrested or turned into an orbit which would keep it forever flying within the limits of the visible universe. A famous example of these speeding stars is 1830 Groombridge, a star of only the 6th magnitude and consequently just visible to the naked eye, whose motion across the line of sight is so rapid that it moves upon the face of the sky a distance equal to the apparent diameter of the moon every 280 years. The distance of this star is at least 200 trillion miles, and may be 2 or 3 times greater, so that its actual speed cannot be less than 200 and may be as much as 400 miles per second. It could be turned into a new course by a close approach to a great sun, but it could only be stopped by collision, head-on, with a body of enormous mass. Barring such accidents, it must, as far as we can see, keep on until it has traversed our stellar system, whence it may escape and pass out into space beyond, to join, perhaps, one of those other universes of which we have spoken. Arcturus, one of the greatest suns in the universe, is also a runaway, whose speed of flight has been estimated all the way from 50 to 200 miles per second. Arcturus, we have every reason to believe, possesses hundreds of times the mass of our sun. Think, then, of the prodigious momentum that its motion implies. Sirius moves more moderately, its motion across the line of sight amounting to only 10 miles per second, but it is at the same time approaching the sun at about the same speed, its actual velocity in space being the resultant of the two displacements. What has been said about the motion of Sirius brings us to another aspect of the subject. The fact is that in every case of stellar motion, the displacement that we observe represents only a part of the actual movement of the star concerned. There are stars whose motion carries them straight toward or straight away from the Earth, and such stars, of course, show no cross motion. But the vast majority are traveling in paths inclined from a perpendicular to our line of sight. Taken as a whole, the stars may be said to be flying about like the molecules in a mass of gas. The discovery of the radial component in the movements of the stars is due to the spectroscope. If a star is approaching, its spectral lines are shifted toward the violet end of the spectrum by an amount depending upon the velocity of the approach. If it is receding, the lines are correspondingly shifted toward the red end. Spectroscopic observation, then, combined with micrometric measurements of the cross motion, enables us to detect the real movement of the star in space. Sometimes it happens that a star's radial movement is periodically reversed. First it approaches, and then it recedes. This indicates that it is revolving around a nearby companion, which is often invisible, and superposed upon this motion is that of the two stars concerned, which together may be approaching or receding or traveling across the line of sight. Thus, the complications involved in the stellar motions are often exceedingly great and puzzling. Yet another source of complication exists in the movement of our own star, the Sun. There is no more difficult problem in astronomy than that of disentangling the effects of the solar motion from those of the motions of the other stars. But the problem, difficult as it is, has been solved, and upon its solution depends our knowledge of the speed and direction of the movement of the solar system through space. For of course, the Sun carries its planets with it. One element of the solution is found in the fact that, as a result of perspective, the stars toward which we are going appear to move apart toward all points of the compass, while those behind appear to close up together. Then the spectroscopic principle already mentioned is invoked for studying the shift of the lines, which is toward the violet in the stars ahead of us, and toward the red in those that we are leaving behind. Of course, the effects of the independent motions of the stars must be carefully excluded. The result of the studies devoted to this subject is to show that we are traveling at a speed of 12 to 15 miles per second in a northerly direction toward the border of the constellations Hercules and Lyra. A curious fact is that the more recent estimates show that the direction is not very much out of a straight line drawn from the Sun to the star Vega, one of the most magnificent suns in the heavens. But it should not be inferred from this that Vega is drawing us on. It is too distant for its gravitation to have such an effect. Many unaccustomed thoughts are suggested by this mighty voyage of the solar system. Whence have we come, and whither do we go? Every year of our lives we advance at least 375 million miles. Since the traditional time of Adam, the sun has led its planets through the wastes of space, no less than 225 billion miles, or more than 2,400 times the distance that separates him from the earth. Go back in imagination to the geologic ages and try to comprehend the distance over which the earth has flown. Where was our little planet when it emerged out of the clouds of chaos? Where was the sun when his thunder march began? What strange constellations shone down upon our globe when its masters of life were the monstrous beasts of the age of reptiles? A million years is not much of a span of time in geologic reckoning, yet a million years ago the Earth was farther from its present place in space than any of the stars with a measurable parallax are now. It was more than 7 times as far as Sirius, nearly 14 times as far as Alpha Centauri, 3 times as far as Vega, and twice as far as Arcturus. But some geologists demand 200, 300, even 1,000 million years to enable them to account for the evolutionary development of the Earth and its inhabitants. In 1,000 million years, the Earth would have traveled farther from the remotest conceivable depths of the Milky Way. Other curious reflections arise when we think of the form of the Earth's track as it follows the lead of the sun in a journey which has neither known beginning nor conceivable end. There are probably many minds which have found a kind of consolation in the thought that every year the globe returns to the same place, on the same side of the sun. This idea may have an occult connection with our traditional regard for anniversaries. When that period of the year returns at which any great event in our lives has occurred, we have the feeling that the Earth, in its annual round, has, in a manner, brought us back to the scene of that event. We think of the Earth's orbit as a well-worn path, which we traverse many times in the course of a lifetime. It seems familiar to us, and we grow to have sort of attachment to it. The sun we are accustomed to regard as a fixed center in space, like the mill or pump around which the harnessed patient mule makes its endless circuits. But the real fact is that the Earth never returns to the place in space where it has once quitted. In consequence of the motion of the sun carrying the Earth and the other planets along, the track pursued by our globe is a vast spiral in space, continually developing and never returning upon its course. It is probable that the tracks of the sun and the other stars are also irregular and possibly spiral, although as far as can be at present determined, they appear to be practically straight. Every star, wherever it may be situated, is attracted by its fellow stars from many sides at once, and although the force is minimized by distance, yet in the course of many ages, its effects must become manifest. Looked at from another side, is there not something immensely stimulating and pleasing to the imagination in the idea of so stupendous a journey, which makes all of us the greatest of travelers? In the course of a long life, a man is transported through space 30,000 million miles. Halley's Comet does not travel 1/4 as far in making one of its immense circuits. And there are adventures on this voyage of which we are just beginning to learn to take account. Space is full of strange things, and the Earth must encounter some of them as it advances through the unknown. Many singular speculations have been indulged in by astronomers concerning the possible effects upon the Earth of the varying state of the space that it traverses. Even the alternation of hot and glacial periods has sometimes been ascribed to this source. When tropical life flourished around the poles, as the remains in the rocks assure us, the needed high temperature may, it has been thought, have been derived from the presence of the Earth in a warm region of space. Then, too, there is a certain interest for us in the thought of what our familiar planet has passed through. We cannot but admire it for its long journey, as we admire the traveler who comes to us from remote and unexplored lands, or as we gaze with a glow of interest upon the first locomotive that has crossed a continent, or a ship that has visited the Arctic or the Antarctic regions. If we may trust the indications of the present course, the Earth, piloted by the Sun, has come from the Milky Way in the far south and may eventually rejoin that mighty band of stars in the far north. While the stars, in general, appear to travel independently of one another, except when they are combined in binary or trinary systems, there are notable exceptions to this rule. In some quarters of the sky, we behold veritable migrations of entire groups of stars whose members are too widely separated to show any indications of revolution about a common center of gravity. This leads us back again to the wonderful group of Pleiades. All of the principal stars composing that group are traveling in virtually parallel lines. Whatever force set them going evidently acted upon all alike. This might be explained by the assumption that when the original projective force acted upon them, they were more closely united than they are at present, and that in drifting apart they have not lost the impulse of the primal motion. Or it may be supposed that they are carried along by some current in space, although it would be exceedingly difficult, in the present state of our knowledge, to explain the nature of such a current. Yet the theory of a current has been proposed. As to an attractive center around which they might revolve, none has been found. Another instance of similar star drift is furnished by 5 of the 7 stars constituting the figure of the Great Dipper. In this case, the stars concerned are separated very widely, the 2 extreme ones by not less than 15 degrees, so that the idea of a common motion would never have been suggested by their aspect in the sky. And the case becomes the more remarkable from the fact that among and between them there are other stars, some of the same magnitude, which do not share their motion, but are traveling in other directions. Still, other examples of the same phenomenon are found in other parts of the sky. Of course, in the case of compact star clusters, it is assumed that all the members share a like motion of translation through space, and the same is probably true of dense star swarms and star clouds. The whole question of star drift has lately assumed a new phase, in consequence of the investigations of Kapteyn, Dyson, and Eddington on the systematic motions of the stars. This research will, it is hoped, lead to an understanding of the general law governing the movements of the whole body of stars constituting the visible universe. Taking about 1,100 stars whose proper motions have been ascertained with an approach to certainty and which are distributed in all parts of the sky, it has been shown that there exists an apparent double drift in 2 independent streams moving in different and nearly opposed directions. The apex of the motion of what is called Stream 1 is situated, according to Professor Kapteyn, in right ascension 85 degrees, declination south 11 degrees, which places it just south of the constellation Orion, while the apex of Stream 2 is in right ascension 260 degrees, declination south 48 degrees, placing it in the constellation Era, south of Scorpio. The 2 apices differ very nearly 180 degrees in right ascension and about 120 degrees in declination. The discovery of these vast star streams, if they really exist, is one of the most extraordinary in modern astronomy. It offers the correlation of stellar movements needed as the basis of a theory of those movements, but it seems far from revealing a physical cause for them. As projected against the celestial sphere, the stars forming the 2 opposite streams appear intermingled, some obeying one tendency and some the other. As Professor Dyson has said, the hypothesis of this double movement is a revolutionary character and calls for further investigation. Indeed, it seems at first glance not less surprising than would be the observation that in a snowstorm the flakes over our heads were divided into two parties and driving across each other's course in nearly opposite directions, as if urged by interpenetrating winds. But whatever explanation may eventually be found for the motions of the stars, the knowledge of the existence of those motions must always afford a new charm to the contemplative observer of the heavens, for they impart a sense of life to the starry system that would otherwise be lacking. A stagnant universe, with every star fixed immovably in its place, would not content the imagination or satisfy our longing for ceaseless activity. The majestic grandeur of the evolutions of the celestial hosts, the inconceivable vastness of the fields of space in which they are executed, the countless numbers, the immeasurable distances, the involved convolutions, the flocking and the scattering, the interpenetrating marches and countermarches, the strange community of impulsion affecting stars that are wide apart in space and causing them to traverse the general movement about them like aids and dispatch bearers on a battlefield, all these arouse an intensity of interest which is heightened by the mystery behind them. End of Chapter 3.
Chapter 4 of Curiosities of the Sky. The Passing of the Constellations. From a historical and picturesque point of view, one of the most striking results of the motions of the stars described in the last chapter is their effect upon the forms of the constellations, which have been watched and admired by mankind for a period so early that the date of their invention is now unknown. The constellations are formed by chance combinations of conspicuous stars, like figures in a kaleidoscope, and if our lives were more commensurate with the eons of cosmic existence, we should perceive that the kaleidoscope of the heavens was ceaselessly turning and throwing the stars into new symmetries. Even if the stars stood fast, the motion of the solar system would gradually alter the configurations as the elements of the landscape dissolve and recombine in fresh groupings with the traveler's progress amid them. But with the stars themselves, all in motion at various speeds and in many directions, the changes occur more rapidly. Of course, rapid is here understood in a relative sense. The wheel of human history, to an eye accustomed to the majestic progression of the universe, would appear to revolve with the velocity of a whirling dynamo. Only the deliberation of geological movements can be contrasted with the evolution and devolution of the constellations. And yet this secular fluctuation of the constellation figures is not without keen interest for the meditative observer. It is another reminder of the swift mutability of terrestrial affairs. To the passing glance, which is all that we can bestow upon these figures, they appear so immutable that they have been called into service to form the most lasting records of ancient thought and imagination that we possess. In the forms of the constellations, the most beautiful, and in imaginative quality, the finest mythology the world has ever known has been perpetuated. Yet in a broad sense, this scroll of human thought imprinted on the heavens is an evanescent of the summer clouds. Although more enduring than parchment, tombs, pyramids, and temples, it is far as they from truly eternalizing the memory of what man has fancied and done. Before studying the effects that the motions of the stars have had and will have upon the constellations, it is worthwhile to consider a little further the importance of the stellar pictures as archives of history. To emphasize the importance of these effects, it is only necessary to recall that the constellations register the oldest traditions of our race. In the history of primeval religions, they are the most valuable documents. Leaving out of account for a moment the more familiar mythology of the Greeks, based on something older yet, we may refer for illustration to that of the mysterious Maya race of America. At Izamal in Yucatan, says Mr. Stansbury Hagar, is a group of ruins perched, after the Mexican and Central American plan, on the summits of pyramidal mounds which mark the site of an ancient Theogonic center of the Mayas. Here, the temples all evidently refer to a cult based upon the constellation as symbols. The figures and the names, of course, were not the same as those that we have derived from our Aryan ancestors, but the star groups were the same, or nearly so. For instance, the loftiest of the temples at Ismail was connected with the sign of the constellation known to us as Cancer, marking the place of the sun at the summer solstice, at which period the sun was supposed to descend at noon like a great bird of fire and consume the offerings left upon the altar. Our Scorpio was known to the Mayas as a sign of the death god. Our Libra, the balance, with which the idea of a divine weighting out of justice has always been connected, seems to be identical with the Mayan constellation Taithalua, with which was associated a temple where dwelt the priest whose special business it was to administer justice and to foretell the future by means of information obtained from the spirits of the dead. Orion, the hunter of our celestial mythology, was among the Mayas a warrior, while Sagittarius and others of our constellation were known to them under different names, of course, and all were endowed with a religious symbolism, and the same star figures, having the same significance, were familiar to the Peruvians, as shown by the temples at Cusco. Thus, the imagination of ancient America sought in the constellation symbols of the unchanging gods. But, in fact, there is no nation and no people that has not recognized the constellations, at one period or another in the history, employed them in some symbolic representative capacity. As handled by the Greeks from prehistoric times, the constellation myths became the very soul of poetry. The imagination of that wonderful race idealized the principal star groups so effectively that the figures and traditions thus attached to them have, for civilized mankind, displaced all others, just as Greek art in its highest forms stands without parallel and eclipses every rival. The Romans translated no heroes and heroines of the mythical period of their history to the sky, and deified Caesars never entered that lofty company, but the heavens are filled with the very early myths of the Greeks. Heracles nightly resumes his mighty labors in the stars. Zeus, in the form of the white bull, Taurus, bears the fair Europa on his back through the celestial waves. Andromeda stretches forth her shackled arms in the star-gemmed ether, beseeching aid, and Perseus, in a blaze of diamond armor, revives his heroic deeds amid sparkling clouds of stellar dust. There too sits Queen Cassiopeia in her dazzling chair, while the great king, Cepheus, towers gigantic over the pole. Professor Young has significantly remarked that a great number of the constellations are connected in some way or other with the Argonautic expedition, that strangely fascinating legend of earliest Greek story which has never lost its charm for mankind. In view of all this, we may well congratulate ourselves that the constellations will outlast our time, and the time of countless generations to follow us, and yet they are very far from being eternal. Let us now study some of the effects of the stellar motions upon them. We begin with the familiar figure of the Great Dipper. He who has not drunk inspiration from its celestial bowl is not yet admitted into the circle of Olympus. This figure is made up of 7 conspicuous stars in the constellation Ursa Major, the Greater Bear. The handle of the Dipper corresponds to the tail of the imaginary bear, and the bowl lies upon his flank. In fact, the figure of a dipper is so evident, and that of a bear so unevident, that to most persons the Great Dipper is the only part of the constellation that is recognizable. Of the 7 stars mentioned, 6 are of nearly equal brightness, ranking as of the 2nd magnitude, while the 7th is of only the 3rd magnitude. The difference is very striking, since every increase in 1 magnitude involves an increase of 2.5 times in brightness. There appears to be little doubt that the faint star, which is situated at the junction of the bowl and the handle, is a variable of long period, since 300 years ago it was as bright as its companions. However that may be, its relative faintness at the present time interferes but little with the perfection of the Dipper's figure. In order the more readily to understand the changes which are taking place, it will well be to mention both the names and the Greek letters which are attached to the 7 stars. Beginning at the star in the upper outer edge of the rim of the bowl, and running in regular order around the bottom and then out to the end of the handle. The names and letters are as follows: Dubhe, Merak, Fayed, Megrez, Aliol, Mizar, Banash. Megrez is the faint star already mentioned at the junction of the bowl and the handle, and Mizar, in the middle of the handle, has a close naked-eye companion which is named Alkar. The Arabs called this singular pair of stars the horse and rider. Merak and Dure are called the pointers because an imaginary line drawn northward through them indicates the pole star. Now it has been found that 5 of these stars, Merak, Fered, Megrez, Aliyah, Mizar, with its comrade, are moving with practically the same speed in an easterly direction, while the other 2, Dublay and Mirash, are simultaneously moving westward, the motions of Banash being apparently more rapid. The consequence of these opposed motions is, of course, that the figure of the Dipper cannot always have existed and will not continue to exist. In the accompanying diagrams, it has been thought interesting to show the relative positions of these 7 stars, as seen from the point which the Earth now occupies, both in the past and in the future. Arrows attached to the stars and the figure representing the present appearance of the Dipper indicate the directions of the motions and the distances over which they carry the stars in a period of about 500 centuries. The time, no doubt, seems long, but remember the vast stretch of ages through which the Earth has passed, and then reflect that no reason is apparent why our globe should not continue to be a scene of animation for 10,000 centuries yet to come. The fact that the little star, Alcor, placed so close to Mizar, should accompany the latter in its flight is not surprising, but that the 2 of the principal stars of the group should be found moving in a direction directly opposed to that pursued by the other 5 is surprising in the highest degree, and it recalls the strange theory of a double drift affecting all the stars, to which attention was called in the preceding chapter. It would appear that Banash and Due belong to one current, and Merak, Fayed, Megrez, Aliyah, and Mizar to the other. As far as is known, the motion of the 7 stars are not shared by the smaller stars scattered about them, but on the theory of currents, there should be such a community of motion, and further investigation may reveal it. From the Great Dipper, we turn to a constellation hardly less conspicuous, and situated at an equal distance from the pole on the other side, Cassiopeia. The famous star group commemorating the romantic queen of Ethiopia, whose vain boasting of her beauty was punished by the exposure of her daughter, Andromeda, to the sea monster, is well marked by 5 stars which form an irregular letter W, with its open side towards the pole. 3 of these stars are usually ranked as of the 2nd magnitude, and 2 of the 3rd, but to ordinary observation, they appear of nearly equal brightness and present a very striking picture. They mark out the chair and part of the figure of the beautiful queen. Beginning at the right hand or western end of the W, their Greek letter designations are beta, alpha, gamma, delta, and epsilon. 4 of them, beta, alpha, delta, and epsilon, are traveling eastwardly at various speeds, while the 5th, gamma, moves in a westerly direction. The motion of beta is more rapid than that of any of the others. It should be said, however, that no little uncertainty attaches to the estimates of the rate of motion of stars, which are not going very rapidly, and different observers often vary considerably in their results. In the beautiful Northern Crown, one of the most perfect and charming of all the figures to be found in the stars, the alternate combining and scattering effects of the stellar motions are shown by comparing the appearance at which the constellation must have had 500 centuries ago with that which it has at present and that which it will have in the future. The 7 principal stars of the asterism, forming a surprisingly perfect coronet, have movements in 3 directions at right angles to one another. That, in these circumstances, they should ever have arrived at positions giving them so striking an appearance of definite association is certainly surprising. From its aspect, one would have expected to find a community of movement governing the brilliance of the crown, but instead of that, we find evidence that they will inevitably drift apart and the beautiful figure will dissolve. A similar fate awaits such asterisms as the Northern Cross and Cygnus, the Crow, which stands on the back of the great sea serpent Hydra and pecks at its scales, Job's coffin, Delphinus, the great square of Pegasus, the twins, Gemini, the beautiful sickle in Leo, and the exquisite group of the Hyades in Taurus. In the case of the Hyades, two controlling movements are manifest. One, affecting 5 of the stars, which form the well-known figure of the letter V, is directed northerly. The other, which controls the direction of 2 stars, has an easterly trend. The chief star of the group, Aldebaran, one of the finest of all stars, both for its brilliance and its color, is the most affected by the easterly motion. In time, it will drift entirely out of connection with its present neighbors. Although Hyades do not form so compact a group as the Pleiades in the same constellation, yet their appearance and relationship is sufficient to awake a feeling of surprise over the fact that, as with the other stars of the Dipper, their association is only temporary or apparent. The great figure of Orion appears to be more lasting, not because its stars are physically connected, but because of their great distance, which renders their movements too deliberate to be exactly ascertained. 2 of the greatest of its stars, Betelgeuse and Rigel, possess, as far as has been ascertained, no perceptible motion across the line of sight. But there is little movement perceptible in the belt. At the present time, this consists of an almost perfect straight line, a row of second magnitude stars, about equally spaced, and the most striking beauty. In the course of time, however, the 2 right-hand stars, Mitaka and Analam, how fine are these Arabic streams, will approach each other and form a naked-eye double. But the third, Alnita, will drift away eastward, so that the belt will no longer exist. For one more example, let us go to the southern hemisphere, whose most celebrated constellation, the Southern Cross, has found a place in all modern literatures, although it has no claim to consideration on account of association with ancient legends. This most attractive asterism, which has never ceased to fascinate the imagination of Christendom since it was first devoutly described by the early explorers of the South, is but a passing collocation of brilliant stars. Yet even in its transfigurations, it has been for hundreds of centuries and will continue to be for hundreds of centuries to come, a most striking object in the sky. Our figures show its appearance in 3 successive phases. First, as it was 50,000 years ago, viewed from the Earth's present location. Second, as it is in our day, and third, as it will be in equal time in the future. The nearness of these bright stars to one another, the length of the longer beam of the cross is only 6 degrees, makes this group very noticeable, whatever the arrangement of its components may be. The largest star, at the base of the cross, is of only the 1st magnitude. 2 of the others are of the 2nd magnitude, and the 4th is of the 3rd. Other stars not represented in the figures increase the effect of the celestial blazonry, although they do not help the resemblance to a cross. But since the motion of the solar system itself will, in the course of so long a period as 50,000 years, produce a great change in the perspective of the heavens, as seen from the Earth, by carrying us nearly 19 trillion miles from our present place, why, it may be asked, seek to represent future appearances of the constellations, which we could not hope to see, even if we could survive so long? The answer is, because these things aid the mind to form a picture of the effects of the motility of the starry universe. Only by showing the changes from some definite point of view can we arrive at a due comprehension of them. The constellations are more or less familiar to everybody, so the impending changes of their forms must at once strike the eye and the imagination, and make clearer the significance of the movements of the stars. If the future history of mankind is to resemble its past, and if our race is destined to survive yet 1,000,000 years, then our remote descendants will see a new heavens, if not a new earth, and will have to invent novel constellations or perpetuate their legends and mythologies. If our knowledge of the relative distances of the stars were more complete, It would be an interesting exercise in celestial geometry to project the constellations probably visible to inhabitants of worlds revolving around some of the other suns of space. Our sun is too insignificant for us to think that he can make a conspicuous appearance among them, except perhaps in a few cases. As seen, for instance, from the nearest known star, Alpha Centauri, the sun would appear to average the first magnitude, and consequently from that standpoint, he might be given a gem of some little constellation which had no Sirius or Arcturus or Vega to eclipse him with its superior splendor. But from the distance of the massive majority of the stars, the sun would probably be invisible to the naked eye, and as seen from nearer systems, can only rank as a 5th or 6th magnitude star, unnoticed and unknown except by the star-charting astronomer. End Chapter 4.
Chapter 5. Conflagrations in the Heavens. Suppose it were possible for the world to take fire and burn up, as some pessimists think that it will do, when the divine wrath shall have sufficiently accumulated against it. Nobody out of our own little corner of space would ever be aware of the catastrophe. With all their telescopes, the astronomers living in the golden light of Arcturus or the diamond blaze of Canopus would be unable to detect the least glimmer of the conflagration that had destroyed the seat of Adam and his descendants, just as now they are totally ignorant of its existence. But at least 15 times in the course of recorded history, men looking out from the earth have beheld in the remote depths of space great outbursts of fiery light, some of them more splendidly luminous than anything else in the firmament except the sun. If they were conflagrations, how many million worlds like ours were required to feed their blaze? It is probable that temporary or new stars, as these wonderful apparitions are called, really are conflagrations, not in the sense of a bonfire or a burning house or city, but in that of a sudden eruption of inconceivable heat and light, such as would result from the stripping off the shell of an encrusted sun, or the crashing together of two mighty orbs flying through space with 100 times the velocity of the swiftest cannon shot. Temporary stars are the rarest and most erratic of astronomical phenomena. The earliest records relating to them are not very clear, and we cannot in every instance be certain that it was one of these appearances that the ignorant and superstitious old chroniclers are trying to describe. The first temporary star that we are absolutely sure of appeared in 1572, and is known as Tycho's star, because the celebrated Danish astronomer, whose remains, with his gold and silver artificial nose, made necessary by a duel, still intact, were disinterred and reburied in 1901, was the first to perceive it in the sky, and the most assiduous and successful in his studies of it. As the first fully accredited representative of its class, this new star made its entry upon the scene without becoming a clap. It is characteristic of these phenomena that they burst into view with amazing suddenness, and, of course, entirely unexpectedly. Tycho's star appeared in the constellation Cassiopeia, near a now well-known and much-watched little star named Kappa, on the evening of November 11, 1572. The story has often been repeated, but it never loses interest, how Tycho, going home that evening, saw people in the street pointing and staring at the sky, directly over their heads, and following the direction of their hands and eyes, he was astonished to see, near the zenith, an unknown star of surpassing brilliance. It outshone the planet Jupiter, and was therefore far brighter than the first magnitude. There was not another star in the heavens that could be compared with it in splendor. Tycho was not in all respects free from the superstitions of his time, and who is? But he had the true scientific instinct, and immediately he began to study the stranger, and to record with the greatest care every change in its aspect. First he determined as well as he could, with the imperfect instruments of his day, many of which he himself had invented, the precise location of the phenomena in the sky. Then he followed the changes that it underwent. At first it brightened until its light equaled or exceeded that of the planet Venus at her brightest, a statement which will be appreciated at its full value by anyone who has ever watched Venus when she plays her dazzling role of evening star, flaring like an arc light in the sunset sky. It even became so brilliant as to be visible in full daylight, since, its position being circumpolar, it never set in the latitude of northern Europe. Finally, it began to fade, turning red as it did so, and in March 1574 it disappeared from Tycho's searching gaze, and has never been seen again from that day to this. None of the astronomers of the time could make anything of it, they had not yet as many bases of speculation as we possess today. Tycho's star has achieved a romantic reputation by being fancifully identified with the Star of Bethlehem, said to have led the wandering Magi from their eastern deserts to the cradle manger of the Savior in Palestine. Many attempts have been made to connect this traditional star with some known phenomenon of the heavens, and none seems more idle than this. Yet it persistently survives, and no astronomer is free from eager questions about it, addressed by people whose imagination has been excited by the legend. It is only necessary to say that the supposition of a connection between the phenomenon of the Magi and Tycho's star is without any scientific foundation. It was originally based on an unwarranted assumption that the star of Tycho was a variable of long period, appearing once every 315 years or thereabout. If that were true, there would have been an apparition somewhere near the traditional date of the birth of Christ, a date which is itself uncertain. But even the data on which the assumption was based are inconsistent with the theory. Certain monkish records speak of something wonderful appearing in the sky in the years 1264 and 945, and these were taken to have been outbursts of Tycho's star. Investigation shows that the records more probably refer to comets, but even if the objects seen were temporary stars, their dates do not suit the hypothesis. From 945 to 1264, there is a gap of 319 years. From 1264 to 1572, one of only 308 years. Moreover, 337 years have now, in 1909, elapsed since Tycho saw the last glimmer of his star. Upon a variability so irregular and uncertain as that, even if we felt sure that it existed, no conclusion could be found concerning an apparition occurring 2,000 years ago. In the year 1600, the year in which Giordano Bruno was burned at the stake for teaching that there is more than one physical world, a temporary star of the third magnitude broke out in the constellation Cygnus, and curiously enough, considering the rarity of such phenomena, only 4 years later, another surprisingly brilliant one appeared in the constellation Ophiuchus. This is often called Kepler's star, because the great German astronomer devoted to it the same attention that Tycho had given to the earlier phenomenon. It too, like Tycho's, was at first the brightest object in the stellar heavens, although it seems never to have quite equaled its famous predecessor in splendor. It disappeared after a year, also turning of a red color as it became more faint. We shall see the significance of this as we go on. Some of Kepler's contemporaries suggested that the outburst of this star was due to a meeting of atoms in space, an idea bearing a striking resemblance to the modern theory of astronomical collisions. In 1670, 1848, and 1860, temporary stars made their appearance, but none of them was of great brilliance. In 1866, one of the second magnitude broke forth in the Northern Crown, and awoke such interest because by that time the spectroscope had begun to be employed in studying the composition of the stars, and Huggins demonstrated that the new star consisted largely of incandescent hydrogen. But this star, apparently unlike the others mentioned, was not absolutely new. Before its outburst, it had shown as a star of the 9th magnitude, entirely invisible, of course, to the naked eye, and after about 6 weeks it faded to its original condition, in which it has ever since remained. In 1876, a temporary star appeared in the constellation Cygnus, and attained at one time the brightness of the 2nd magnitude. Its spectrum and its behavior resembled those of its immediate predecessor. In 1885, astronomers were surprised to see a 6th magnitude star glimmering in the midst of the hazy cloud of the great Andromeda Nebula. It soon absolutely disappeared. Its spectrum was remarkable for being continuous, like that of the nebula itself. A continuous spectrum is supposed to represent a body, or a mass, which is either solid or liquid, or composed of gas under great pressure. In January 1892, a new star was suddenly seen in the constellation Auriga. It never rose much above the 4th magnitude, but it showed a peculiar spectrum containing both bright and dark lines of hydrogen. But a bewildering surprise was now in store. The world was to behold at the opening of the 20th century such a celestial spectacle as had not been on view since the times of Tycho and Kepler. Before daylight on the morning of February 22, 1901, the Reverend Dr. Anderson of Edinburgh, an amateur astronomer who had also been the first to see the new star in Auriga, beheld a strange object in the constellation Perseus, not far from the celebrated variable star Algol. He recognized its character at once, and immediately telegraphed the news, which awoke the startled attention of astronomers all over the world. When first seen, the new star was no brighter than Algol, less than the second magnitude, but within 24 hours it was ablaze, outshining even the brilliant Capella, and far surpassing the first magnitude. At the spot in the sky where it appeared, nothing whatever was visible on the night before its coming. This is known with certainty, because a photograph had been made of that region on February 21st, and this photograph showed everything down to the 12th magnitude, but not a trace of the stranger, which burst into view between the 21st and the 22nd like the explosion of a rocket. Upon one who knew the stars, the apparition of this intruder in a well-known constellation had the effect of a sudden invasion. The new star was not far west of the zenith in the early evening, and in that position showed to the best advantage. To see Capella, the hitherto unchallenged ruler of that quarter of the sky, abased by comparison with this stranger of alien aspect, for there was always an unfamiliar look about the nova, was decidedly disconcerting. It seemed to portend the beginning of a revolution in the heavens. One could understand what the effect of such an apparition must have been in the superstitious times of Tycho. The star of Tycho had burst forth on the northern border of the Milky Way. This one was on its southern border, some 45 degrees farther east. Astronomers were well prepared this time for the scientific study of the new star, both astronomical photography and spectroscopy having been perfected, and the results of their investigations were calculated to increase the wonder with which the phenomenon was regarded. The star remained at its brightest only a few days, then like a veritable conflagration it began to languish, and, like the reflection of a dying fire, as it sank it began to glow with the red color of embers. But its changes were spasmodic. Once about every 3 days it flared up, only to die away again. During these fluctuations its light varied alternately in the ratio of 1 to 6. Finally it took a permanent downward course, and after a few months the naked eye could no longer perceive it. But it remained visible with telescopes, gradually fading until it had sunk to the 9th magnitude. Then another astonishing change happened. In August, photographs taken at the Yerkes Observatory and at Heidelberg showed that the nova was surrounded by a spiral nebula. The nebula had not been there before, and no one could doubt that it represented a phase of the same catastrophe that had produced the outburst of the new star. At one time the star seemed virtually to have disappeared, as if all its substance had been expanded into the nebulous cloud, but always there remained a stellar nucleus about which the misty spiral spread wider and ever wider, like a wave expanding around a center of disturbance. The nebula, too, showed a variability of brightness, and 4 condensations which formed in it seemed to have a motion of revolution about the star. As time went on, the nebula continued to expand at a rate which was computed to be not less than 20,000 miles per second. And now the star itself, showing indications of having turned into a nebula, behaved in a most erratic manner, giving rise to the suspicion that it was about to burst out again. But this did not occur, and at length it sunk into a state of lethargy from which it has to the present time not recovered. But the nebulous spiral has disappeared, and the entire phenomena as it now, in 1909, exists, consists of a faint nebulous star of less than the 9th magnitude. The wonderful transformations just described had been forecast in advance of the discovery of the nebulous spiral encircling the star by the spectroscopic study of the latter. At first there was no suggestion of a nebular constitution, but within a month or two characteristic nebular lines began to appear, and in less than 6 months the whole spectrum had been transformed to the nebular type. In the meantime, the shifting of the spectral lines indicated a complication of rapid motions in several directions simultaneously. These motions were estimated to amount from 100 to 500 miles per second. The human mind is so constituted that it feels forced to seek an explanation of so marvelous a phenomenon as this, even in the absence of the data needed for a sound conclusion. The most natural hypothesis, perhaps, is that of a collision. Such a catastrophe could certainly happen. It has been shown, for instance, that in the infinity of time, the Earth is sure to be hit by a comet. In the same way, it may be asserted that, if no time limit is fixed, the Sun is certain to run against some obstacle in space, either another star, or a dense meteor swarm, or one of the dark bodies which there is every reason to believe abound around us. The consequences of such a collision are easy to foretell, provided that we know the masses and the velocities of the colliding bodies. In a preceding chapter we have discussed the motions of the Sun and stars, and have seen that they are so swift that an encounter between any two of them could not but be disastrous. But this is not all, for as soon as two stars approach within a few million miles, their speed would be enormously increased by their reciprocal attractions, and, if their motion was directed radially with respect to their centers, they would come together with a crash that would reduce them both to nebulous clouds. It is true that the chances of such a head-on collision are relatively very small. Two stars approaching each other would most probably fall into closed orbits around their common center of gravity. If there were a collision, it would most likely be a grazing one instead of a direct front-to-front encounter. But even a close approach, without any actual collision, would probably prove disastrous, owing to the tidal influence of each of the bodies on the other. Suns, in consequence of their enormous masses and dimensions, and the peculiarities of their constitution, are exceedingly dangerous to one another at close quarters. Propinquity awakes in them a mutually destructive tendency. Consisting of matter in the gaseous, or perhaps in some cases liquid state, their tidal pull upon each other, if brought close together, might burst them asunder, and the photospheric envelope being destroyed, the internal incandescent mass would gush out, bringing fiery death to any planets that were revolving near. Without regard to the resulting disturbance of the Earth's orbit, the close approach of a great star to the Sun would be in the highest degree perilous to us. But this is a danger which may properly be regarded as indefinitely remote, since at our present location in space, we are certainly far from every star except the Sun, and we may feel confident that no great invisible body is near, for if there were one, we should be aware of its presence from the effects of its attraction. As to dark nebulae, which may possibly lie in the track that the solar system is pursuing at the rate of 375 million miles per year, that is another question, and they too could be dangerous. This brings us back directly to Nova Persei, for among the many suggestions offered to explain its outburst, as well as those of other temporary stars, one of the most fruitful is that of a collision between a star and a vast invisible nebula. Professor Seeliger of Munich first proposed this theory, but it afterward underwent some modifications from others. Stated in a general form, the idea is that a huge dark body, perhaps an extinguished sun, encountered in its progress through space a widespread flock of small meteors, forming a dark nebula. As it plunged into the swarm, the friction of the innumerable collisions with the meteors heated its surface to incandescence, and being of vast size, it then became visible to us as a new star. Meanwhile, the motion of the body through the nebula, and its rotation upon itself, set up a gyration in the blazing atmosphere formed around it by the vaporized meteors, and as this atmosphere spread wider, under the laws of gyratory motion, a rotation in the opposite direction began in the inflamed meteoric cloud, outside the central part of the vortex. Thus the spectral lines were caused to show motion in opposite directions, a part of the incandescent mass approaching the Earth simultaneously with the retreat of another part. So the curious spectroscopic observations before mentioned were explained. This theory might also account for the appearance of the nebulous spiral first seen some 6 months after the original outburst. The sequent changes in the spectrum of the nova are accounted for by this theory on the assumption, reasonable enough in itself, that at first the invading body would be enveloped in a vaporized atmosphere of relatively slight depth, producing by its absorption the fine dark lines first observed, but that as time went on and the incessant collisions continued, the blazing atmosphere would become very deep and extensive, whereupon the appearance of the spectral lines would change, and bright lines due to the light of the incandescent meteors surrounding the nucleus at a great distance would take the place of the original dark ones. The vortex of meteors once formed would protect the flying body within from further immediate collisions, the latter now occurring mainly among the meteors themselves, and then the central blaze would die down, and the original splendor of the phenomenon would fade. But the theories about Nova Persei have been almost as numerous as the astronomers who have speculated about it. One of the most startling of them assumed that the outburst was caused by the running amok of a dark star, which had encountered another star surrounded with planets, the renewed outbreaks of light after the principal one had faded being due to the successive running down of the unfortunate planets. Yet another hypothesis is based on what we have already said of the tidal influence that two close approaching suns would have upon each other. Supposing two such bodies, which had become encrusted, but remained incandescent and fluid within, to approach within almost striking distance. They would whirl each other about their common center of gravity, and at the same time their shells would burst under the tidal strain, and their glowing nuclei being disclosed would produce a great outburst of light. Applying this theory to a nova like that of 1866 in the Northern Crown, which had been visible as a small star before the outbreak, and which afterward resumed its former aspect, we should have to assume that a yet shining sun had been approached by a dark body whose attraction temporarily burst open its photosphere. It might be supposed that in this case, the dark body was too far advanced in cooling to suffer the same fate from the tidal pull of its victim, but a close approach of that kind would be expected to result in the formation of a binary system, with orbits of great eccentricity, perhaps, and after the lapse of a certain time, the outburst should be renewed by another approximation of the two bodies. A temporary star of that kind would rather be ranked as variable. The celebrated French astronomer Janssen had a different theory of nova Persei, and of temporary stars in general. According to his idea, such phenomena might be the result of chemical changes taking place in a sun without interference by or collision with another body. Janssen was engaged for many years in trying to discover evidence of the existence of oxygen in the sun, and he constructed his observatory on the summit of Mount Blanc, specially to pursue that research. He believed that oxygen must surely exist in the sun, since we find so many other familiar elements included in the constitution of the solar globe, and as he was unable to discover satisfactory evidence of its presence, he assumed that it existed in a form unknown on the Earth. If it were normally in the sun's chromosphere or coronal atmosphere, he said, it would combine with the hydrogen which we know is there and form an obscuring envelope of water vapor. It exists then in a special state, uncombined with hydrogen, but let the temperature of the sun sink to a critical point, and the oxygen will assume its normal properties and combine with the hydrogen, producing a mighty outburst of light and heat. This, Janssen thought, might explain the phenomena of the temporary stars. It would also, he suggested, account for their brief career, because the combination of the elements would be quickly accomplished, and then the resulting water vapor would form an atmosphere, cutting off the radiation from the star within. This theory may be said to have a livelier human interest than some of the others, since, according to it, the sun may carry in its very constitution a menace to mankind. One does not like to think of it being suddenly transformed into a gigantic laboratory for the explosive combination of oxygen and hydrogen. But while Janssen's theory might do for some temporary stars, it is inadequate to explain all the phenomena of nova Persei, and particularly the appearance of the great spiral nebula that seem to exhale from the heart of the star. Upon the whole, the theory of an encounter between a star and a dark nebula seems best to fit the observations. By that hypothesis, the expanding billow of light surrounding the core of the conflagration is very well accounted for, and the spectroscopic peculiarities are also explained. Dr. Gustave Le Bon offers a yet more alarming theory, suggesting that temporary stars are the result of atomic explosion, but we shall touch upon this more fully in Chapter 14. Twice in the course of this discussion we have called attention to the change of color invariably undergone by temporary stars in the later stages of their career. This was conspicuous with nova Persei, which glowed more and more redly as it faded, until the nebulous light began to overpower that of the stellar nucleus. Nothing could be more suggestive of the dying out of a great fire. Moreover, change of color from white to red is characteristic of all variable stars of long period, such as Mira and Cetus. It is also characteristic of stars believed to be in the later stages of evolution, and consequently approaching extinction, like Antares and Betelgeuse, and still more notably certain small stars which gleam like rubies in the field of the telescope. These last appear to be suns in the closing period of existence as self-luminous bodies. Between the white stars, such as Sirius and Rigel, and the red stars, such as Aldebaran and Alpha Herculis, there is a progressive series of colors from golden yellow through orange to deep red. The change is believed to be due to the increase of absorbing vapors in the stellar atmosphere as the body cools down. In the case of ordinary stars, these changes no doubt occupy many millions of years, which represent the average duration of solar life. But the temporary stars run through similar changes in a few months. They resemble ephemeral insects, born in the morning and doomed to perish with the going down of the sun. End of Chapter 5.
Chapter 6, Explosive and Whirling Nebula. One of the most surprising triumphs of celestial photography was Professor Keeler's discovery in 1899. The great majority of the nebula have a distinctly spiral form. This form, previously known in Lord Rosse's great Whirlpool Nebula, had been supposed to be exceptional. Now the photographs, far excelling telescopic views in the revelation of nebular forms, showed the spiral to be the typical shape. Indeed, it is a question whether all nebula are not to some extent spiral. The extreme importance of this discovery is shown in the effect that it had upon hitherto prevailing views of solar and planetary evolution. For more than 3/4 of the century, Laplace's celebrated hypothesis of the manner of origin of the solar system, from a rotating and contracting nebula surrounding the Sun, had guided speculation on the subject, and had been tentatively extended to cover the evolution of systems in general. The apparent forms of some form of the nebula, which the telescope had revealed, were regarded, and by some are still regarded, as giving visual evidence in favor of this theory. There is a ringed nebula in Lyra, with a central star, and a planetary nebula in Gemini, bearing no little resemblance to the planet Saturn, with its rings, both of which appear to be practical realizations of Laplace's idea, and the elliptical ring surrounding the central condensation of the Andromeda Nebula may be cited for the same kind of proof. But since Keeler's discovery, there had been a decided turning away of speculation another way. The form of the spiral nebula seems to be entirely inconsistent with the theory of an originally globular or disk-based nebula condensing around a sun, throwing off or leaving off rings to be subsequently shaped into planets. Some astronomers, indeed, now reject Laplace's hypothesis in toto, preferring to think that even our solar system originated from a spiral nebula. Since the spiral type prevails among the existing nebula, we must take any mathematical theory of the development of stars and planetary systems from them accord with the requirements which that form imposes. A glance at the extraordinary variations upon the spiral, which Professor Keeler's photographs reveal, is sufficient to convince one of the difficulty of the task of basing a central theory upon them. In truth, it is much easier to criticize Laplace's hypothesis than to invent a satisfactory substitute for it. If the spiral nebula seem to oppose it, there are other nebula which appear to support it, and it may be that no one fixed theory can account for all the forms of stellar evolution in the universe. Our particular planetary system may have originated very much as the great French mathematician supposed, while others have undergone, or are now undergoing, a different process of development. There is always a too strong tendency to regard an important new discovery, and the theories and speculations based upon it, as revolutionizing knowledge, and displacing or overthrowing everything that went before. Upon the plea that Laplace only made a guess, more recent guesses have been driven to extremities and treated by injudicious exponents as the solid facts at last. Before considering more recent theories than Laplace's, let us see what the nature of the photographic revelations is. The vast celestial maelstrom discovered by Lord Rosse in the hunting dogs may be taken as the leading type of the spiral nebula, although there are less conspicuous objects of the kind which perhaps better illustrate some of their peculiarities. Lord Rosse's nebula appears far more wonderful in the photographs than his drawings made with the aid of his giant reflecting telescope at Parsonstown, for the photographic plate records details that no telescope is capable of showing. Suppose we look at the photograph of this object as any person of common sense would look at any great and strange natural phenomenon. What is the first thing that strikes the mind? It is certainly the appearance of violent whirling motion. One would say that the whole glowing mass has been spun out with tremendous velocity, or that it had been set rotating so rapidly that it had become the victim of centrifugal force, one huge fragment having broken loose and started to gyrate off into space. Closer inspection shows that in addition to the principal focus, there are various smaller condensations scattered throughout the mass. These are conspicuous in the spirals. Some of them are stellar points, and but for the significance of their location, we might suppose them to be stars which happen to lie in line between us and the nebula. But when we observe how many of them follow most faithfully the curves of the spirals, we cannot but conclude that they form an essential part of the phenomenon. It is not possible to believe that their presence in such situations is merely fortuitous. One of the outer spirals has at least a dozen of these star-like points sprung upon it, some of them sharp, small, and distinct, others more blurred and nebulous, suggesting the different stages of condensation. Even the part which seems to have been flung loose from the main mass has, in addition to its central condensation, at least one stellar point gleaming in the half-varnished spire attached to it. Some of the more distant stars scattered around the whirlpool look as if they too had been shot out of the mighty vortex, afterward condensing into unmistakable solar bodies. There are at least 2 curved rows of minute stars, a little beyond the periphery of the luminous whirl, which clearly follow lines concentric with those of nebulous spirals. Such facts are simply dumbfounding for anyone who will bestow sufficient thought upon them, for these are suns, though they may be small ones, and what a birth is that for a sun. Look now again at the glowing spirals. We observe that hardly have left the central mass before they begin to coagulate. In some places, they have a ropey aspect, or they are like peace gods filled with growing seeds, which eventually will become stars. The great focus itself shows a similar tendency, especially around its circumference. The sense that it imparts of a tremendous shattering force at work is overwhelming. There is probably more matter in that whirling and busting nebula than would suffice to make 100 solar systems. It must be convinced at once that there is no confirmation of the Laplacian hypothesis here. But what hypothesis will fit the facts? There is one which has been claimed it does so, but we shall come to that later. In the meanwhile, as a preparation, fix in the memory the appearance of that second spiral mass, spinning beside its master, which seems to have spurned it away. For a second example of the spiral nebula, look at the one in the constellation Triangulum. God, how hath the imagination of puny man failed to comprehend thee? Here is creation, through destruction with a vengeance. The spiral form of the nebula is unmistakable, but is half obliterated amid the turmoil, a flying massage hurled away on all sides with tornadic fury. The focus itself is splitting asunder under intolerable strain, and in a little while, as time is reckoned in the cosmos, it will be gyrating into stars, and then look into the cyclonic rain of already finished stars whirling around the outskirts of the storm. Observe how scores of them are yet involved in the fading streams of the nebulous spirals. See how they have been thrown into vast loops and curves, of a beauty that half redeems the terror of the spectacle enclosed within their lines, like iridescent cirri hovering about the edges of a hurricane. And so again are suns born. Let us turn to the exquisite spiral in Ursa Major. How different is its aspect from that of the other? One would say that if the terrific coral in Triangulum has all but destroyed itself in its fury, this one, on the contrary, has just begun its self-demolition. As one gazes, one seems to see it in the swift, smooth acceleration motion that precedes catastrophe. The central part is still intact, dense, and uniform in texture. How graceful are the spirals that smoothly rise from its oval rim, and gemmed with little stars, wind off into the darkness until they have become as delicate as the threads of gossamer. But at the bottom of the story, told here, is the same: creation by gyration. Compare with the above curious mass in Cetus. Here, the plane of whirling nebula nearly coincides with our line of sight, and we see the object at a low angle. It is far advanced and torn to shreds, and if we could look at it perpendicularly to its plane, it is evident that it would closely resemble the spectacle of Triangulum. Then, take the famous Andromeda Nebula, which is so vast that notwithstanding its immense distance, even the naked eye perceives it as the enigmatical wisp in the sky. Its image on the sensitive plate is the masterpiece of astronomical photography. For wild, incomprehensible beauty, there is nothing that can be compared with it. Here, if anywhere, we look upon the spectacle of creation in one of its earliest stages. The Andromeda Nebula is apparently less advanced towards transformation into stellar bodies than that is Triangulum. The immense crowd of stars sprinkled over it and its neighborhood seem in the main to lie this side of the nebula, and consequently have no connection with it. But the incipient stars, in some places clusters of them, are seen in the nebulous rings, while one or two huge masses seem to give promise of transformation into stellar bodies of unusual magnitude. I say rings because although the loops encompassing the Andromeda Nebula have been called spirals by those who wish utterly to demolish Laplace's hypothesis, yet they're not manifestly such as can be seen on comparing them with the undoubted spirals of the Lord Rossum Nebula. They look quite as much like circles or ellipses seen at any angle of, say, 15 or 20 degrees to their plane. If they are truly elliptical, they accord fairly well with Laplace's idea, except that the scale of magnitude is stupendous, and if the Andromeda Nebula is to become a solar system, it will surpass ours in grandeur beyond all possibility of comparison. There is one circumstance connected with the